Are there other universes? It is a quiet question. It does not rush. It does not demand. It simply sits there, almost like it has always been waiting for us. If you look back through history, you will notice something interesting. Long before telescopes, long before rockets, long before we knew that our planet is a small sphere floating in space, people were already imagining other worlds. Ancient storytellers spoke of layered heavens stacked above the sky like floors in a tall building. Some cultures described endless realms, each with its own rules. Others imagined hidden worlds beneath the ground, or distant lands across cosmic oceans. They did not have physics equations. They did not have satellites. But they had imagination. Why? Why does the human mind keep reaching beyond what it can see? Think about standing at the edge of the ocean. You look out, and the water meets the sky. It feels like the world ends there. But deep inside, you know it doesn't. You know there is more beyond that horizon, even if you cannot see it. That feeling may be one of the oldest instincts we have. When early humans looked up at the night sky, they saw thousands of tiny lights. On a clear night away from city lights, you can see about 5,000 stars with your eyes alone. That's like looking at a stadium filled with glowing dots, scattered across the dark ceiling above you. It must have felt impossible that this was all there was. Even now, when you step outside and look up, the sky feels endless. And yet, we know something surprising. What we see is only a tiny slice of what exists. Our galaxy alone, the Milky Way, holds somewhere between 100 billion and 400 billion stars. That's so many that if you tried to count one star every second, without sleeping, it would take you more than 3,000 years just to reach 100 billion. And that's just one galaxy. So here's a gentle question. If there are hundreds of billions of galaxies, each with hundreds of billions of stars, why would there be only one universe? You can almost feel the mind resisting the idea of limits. Children often ask, "What's at the end of space?" And when you answer carefully, space doesn't really have an edge like a wall, the next question comes naturally. But if you keep going forever, what's out there? This curiosity feels built into us. It is the same instinct that made ancient sailors leave the shoreline, the same instinct that made explorers cross deserts and mountains, the same instinct that pushed us to build machines that could leave Earth. We are not comfortable with walls, and maybe that is why the idea of other universes never disappeared. It simply changed shape. In ancient times, other worlds were spiritual or mythical. In the Middle Ages, some thinkers quietly wondered whether God might have created many worlds instead of one. Later, when telescopes showed that stars were not tiny lights stuck to a dome, but distant suns scattered through deep space, the question shifted again. Now it was no longer just imagination, it was possibility. When scientists realized that our sun is just one average star among billions, and that many stars have planets orbiting them, the universe suddenly felt much larger. Planets were not rare jewels, they were common, like grains of sand on a beach, and that changed something inside us. If there are countless planets, maybe there are countless versions of reality too, but where does that leap come from? Why jump from many planets to many universes? Part of it is scale. The observable universe, the part we can see, stretches about 93 billion light-years across. A light-year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second, fast enough to circle the Earth more than 7 times in 1 second. In a single year, it travels about 9.5 trillion kilometers. That's like driving around Earth's equator more than 200 million times. Now imagine 93 billion of those light years, laid side by side. It's almost too large to hold in your mind, like trying to imagine every grain of sand on every beach on Earth, and then multiplying it by millions. When something becomes that large, the mind starts to ask, is this really all of it? Or is this just the part we happen to see? There is also something personal about the question of other universes. Have you ever wondered how different your life might have been if one small choice had changed? If you had turned left instead of right, said yes instead of no, sent the message, or didn't? It's a quiet thought, a simple what if. Now stretch that feeling outward. What if reality itself has branches? What if the story could have unfolded differently on a much larger scale? This is not just science. It touches something deeper, our sense of possibility. Humans are storytellers. We imagine alternatives naturally. When something happens, we picture how it might have gone another way. Our brains are built to explore options. It helps us learn. It helps us survive. So perhaps imagining other universes is not strange at all. Perhaps it is the natural extension of how we think. When we learned that Earth is not the center of everything, it hurt our pride a little. When we learned that our galaxy is not the only galaxy, it shrank us further. Each discovery made us smaller compared to the whole. So here is another gentle question. If we are not at the center of the planet, and not at the center of the solar system, and not at the center of the galaxy, and not even in a special galaxy, why would we assume we are in the only universe? That assumption begins to feel less solid. At the same time, there is something comforting about the idea that there might be more. It suggests that reality is richer than it appears, that existence may not be a single fragile bubble in a void, but part of something much larger. It is like discovering that the small pond you grew up near is connected to rivers, and those rivers connect to oceans. The pond did not disappear. It simply became part of something greater. The idea of other universes is still just an idea, but the reason it keeps returning, in myths, in stories, in physics labs, in quiet late-night thoughts, may tell us something important about ourselves. We seem to sense that what we see cannot be the whole story. And that instinct, that gentle push beyond the horizon, may be one of the most human things about us. The question, are there other universes, is not only about space, it is about limits, and whether they are real. As we continue, we will move slowly and carefully. We will look at what we mean by the word universe in the first place. Because before asking whether there are many, we need to understand what the one we know actually is. For now, just rest in the thought that this question did not begin with modern science. It began with people looking up at the night sky and feeling that quiet pull. The pull toward more, and perhaps that pull is still guiding us. As we move forward, feel free to share where you're listening from, or leave a quick thought below. And if this channel means something to you, subscribing is a small way to support the journey. When we ask, are there other universes? There is a quiet detail hiding inside the question. What exactly do we mean by the word universe? It sounds simple, it feels like a clear word, but when you slow down and look at it closely, it becomes a little more slippery. Most people think of the universe as everything. All of space, all of time, all matter, all energy, every star, every planet, every galaxy, if that is the definition, everything. Then asking about other universes sounds strange, because how can there be something outside of everything? So the first step is to gently untangle this word. In everyday language, the universe often means all that exists. But in modern science, the word is sometimes used in a more practical way. It can mean the region of reality that is connected to us, the part that follows the same physical rules and has shared the same beginning. And that brings us to another idea, the observable universe. This is not the entire universe. It is only the part we can see. Light travels at a certain speed, about 300,000 kilometers per second. That is incredibly fast, fast enough to go around the Earth more than 7 times in 1 second. If you blink, Light could circle the planet many times before your eyelids open again. But even at that speed, light takes time to travel long distances. When you look at the moon, you see it as it was about 1 second ago. When you look at the sun, you see it as it was 8 minutes ago. If the sun suddenly disappeared, which it won't, we would not notice for 8 minutes. Now stretch that idea much farther. Some galaxies are so distant that their light has taken more than 13 billion years to reach us. That means we see them as they were when the universe was very young. Like looking at an old photograph taken billions of years ago. This creates a limit. There is only so far we can see, because the universe has a finite age. If the universe is about 13.8 billion years old, then light has only had 13.8 billion years to travel, so we cannot see anything further than the distance light could cover in that time. But here is where it becomes interesting. Because space itself has been expanding, the observable universe is not just 13.8 billion light-years wide. It is much larger. Today, it stretches about 93 billion light-years across. Imagine a sphere so large that light would need 93 billion years to cross from one side to the other. That number is hard to hold in your mind. If 1 light-year were the length of a single step, 93 billion light-years would be like walking around the entire Earth more times than you could count in a lifetime. And yet, that enormous sphere is only the part we can observe. Beyond it, there may be more space, more galaxies, more stars, but their light has not had enough time to reach us yet. So here is a gentle question. If you are standing in the middle of a thick fog and you can only see a few meters ahead, does that mean the world ends at the edge of the fog? Of course not. The fog is simply blocking your view. In a similar way, the observable universe may be like a glowing bubble around us, defined by how far light has been able to travel. Beyond that bubble, space could continue. We just cannot see it yet. This boundary is sometimes called the cosmic horizon. It is not a wall. It is not a barrier you would crash into. It is simply the edge of what light has had time to show us, and that changes the meaning of universe. Sometimes, when scientists talk about other universes, they do not mean something completely separate in a fantasy sense. They might simply mean regions of space, so far away that we will never see them. Even if space continues forever beyond our observable horizon, those distant regions would still be part of the same overall reality. They would follow the same physical laws. They would share the same origin. So are those other universes, or just distant parts of ours? The answer depends on how we define the word. This is why the question feels tricky. If the universe means absolutely everything that exists, then by definition, there can only be one. But if the universe means a connected region of space-time with shared rules and history, then perhaps there could be many separate regions. It is like asking about oceans. On Earth, we speak of the Pacific Ocean, the Atlantic Ocean, the Indian Ocean. But in truth, they are all connected. It is one continuous body of water with different names. But imagine if there were completely separate oceans on different planets, with no connection at all. Then each would be its own system. So when we ask about other universes, we are really asking, are there completely separate cosmic oceans, disconnected from ours? Or is everything just one vast continuous expanse, far larger than we can see? This leads to another quiet realization. The word universe once meant something smaller. Thousands of years ago, it meant the sky dome above Earth and the ground below. Then it grew to include the sun and planets. Later, it expanded to include the Milky Way. Then it grew again to include billions of galaxies. Each time we thought we understood the size of everything, the boundary moved. It is a humbling pattern. So what if our current idea of the universe, even at 93 billion light-years across, is still just a small part of something larger? What if the observable universe is like one glowing window in a much bigger structure. This is where the idea of other universes begins to take shape, not as pure imagination, but as a possible extension of what we already know. We know our view is limited. We know light has a maximum speed. We know the universe has a finite age. We know space is expanding. Given those facts, it is reasonable to ask whether what we see is only a portion of a larger whole. And once that thought settles in, the question feels less wild. It feels like the next natural step before we can explore the deeper theories about bubbles, branches, and hidden dimensions. We need to stay grounded in this simple truth. Our view of reality has edges, not because reality ends there, but because our light has not yet gone farther. And sometimes, understanding the limits of what we can see is the first step toward imagining what might lie beyond. Feels open, endless, like there is nothing blocking your view. But in truth, you are looking through a kind of window, and that window has limits. Not because something is in the way, not because space suddenly stops, but because light needs time to travel. Everything we see in space comes to us through light. Stars shine, galaxies glow. Even the faint background radiation left over from the early universe reaches us as tiny waves of energy. But light is not instant. It moves incredibly fast, about 300,000 kilometers every second. That is fast enough to circle Earth more than 7 times in a single second. If you could travel that quickly, you could go from New York to Tokyo in less than a blink. And yet, even at that speed, space is so large that light struggles to keep up. Imagine you turn on a flashlight in a dark field. The beam spreads outward. After 1 second, it has traveled 300,000 kilometers. After 1 year, it has traveled about 9.5 trillion kilometers. That distance, 9.5 trillion kilometers, is what we call 1 light year. Now imagine that flashlight has been shining for nearly 14 billion years. That is roughly the age of our universe. So you might think, does that mean we can see 14 billion light years in every direction? It sounds simple, but space has been stretching. While light was traveling toward us, space itself was expanding, like the surface of a balloon being inflated. So the galaxies that sent us their light are now much farther away than they were when that light began its journey. Because of this stretching, the observable universe is not just 14 billion light years across. It is about 93 billion light years wide today. Picture a sphere so vast that even light, the fastest thing we know, would need 93 billion years to cross from one side to the other. If that sphere were shrunk down to the size of Earth, our entire solar system would be smaller than a speck of dust. That is the size of the window we can see through. But here is the quiet part. We cannot see beyond it, not because there is nothing there, but because light from those regions has not had enough time to reach us. Think of it like standing on a hill during a thunderstorm at night. You see flashes of lightning in the distance. Each flash reveals a small portion of the landscape for a brief moment. But beyond the reach of that light, the land still exists. You just cannot see it. In the same way, our cosmic horizon marks the edge of where light has reached us since the beginning of time. So what lies beyond that horizon? Is it empty, or is it more of the same? More galaxies, more stars, stretching on and on. Based on what we understand about physics, there is no strong reason to think space simply ends at that boundary. In fact, most models suggest it likely continues. If the observable universe were like the visible part of the ocean from the beach, then beyond the horizon, the water probably continues. You just cannot see it because the curve of the Earth hides it from view. But here is something subtle. Even if space continues forever beyond our observable region, we may never be able to see those distant areas, because space is expanding. And not just expanding gently, the expansion is accelerating. Imagine 2 ants standing on a rubber sheet. If you stretch the sheet slowly, they move apart. But if you stretch it faster and faster, Eventually, they separate so quickly that neither ant can ever reach the other, no matter how fast they walk. This is similar to what is happening in our universe. Galaxies are moving away from us as space expands. The farther they are, the faster they appear to move away. Some are already moving away so quickly that their light will never reach us in the future. It is as if they are being carried off by a current that is too strong to swim against. This creates a deep limit. There are regions of reality that are simply beyond our ability to observe, not because we lack better telescopes, not because we are not advanced enough, but because the structure of space-time itself prevents it. So here is a natural question. If there are regions we can never see, how do we know they exist at all? The honest answer is, we infer them. When you see a smooth curve on the surface of a lake, you assume the water continues beyond the small patch you are staring at. When you see a forest stretching to the horizon, you assume trees continue beyond your view. In the same way, when we observe that space appears flat and uniform on large scales, like a smooth tabletop extending outward, we suspect that it continues beyond our horizon, but we cannot confirm it directly. And this is where the idea of other universes begins to shift from imagination into serious thought. If our observable universe is just one small region of a much larger reality, then what lies beyond may be similar to what we see, or it might not. The limit of what we can see does something interesting to the mind. It reminds us that knowledge has edges. No matter how powerful our telescopes become, there will always be a boundary set by light and time, and that boundary invites curiosity. If there is more beyond, could it look exactly like our region? Same stars, same laws of physics, just farther away? Or could something change beyond that invisible line? Right now, we do not know, but the simple fact that our view is limited opens the door to possibility. We are inside a vast bubble of visibility, about 93 billion light-years across. Beyond it, space may continue endlessly, or something else may begin. And as we slowly move forward, we will explore how modern physics started to suggest that beyond our horizon might not just be more of the same, but perhaps entirely separate realms, born in ways we are only beginning to understand. For a long time, the idea of other universes belonged mostly to stories and imagination. Scientists were focused on understanding this universe, how it began, how it grew, and how it behaves. The goal was not to multiply realities, it was to explain the one we already see. But sometimes, when you try to solve one mystery, you quietly open the door to another. That is what happened in the late 20th century. Physicists were trying to understand something puzzling about the early universe. When we look far into space, we are also looking far back in time. We see the universe as it was, billions of years ago, and what we observe is surprisingly smooth. No matter where we look, in one direction or the opposite, the universe looks almost the same on very large scales. The temperature of the early radiation, what we call the cosmic microwave background, is nearly identical everywhere, with differences of only a tiny fraction of a degree. Here is why that is strange. If you take two regions of space that are extremely far apart, say on opposite sides of the observable universe, light would not have had enough time to travel between them since the beginning of the universe. They should never have been in contact. They should not have been able to share information. And yet, they look almost identical. It is like finding two ovens on opposite sides of a city that somehow baked their cakes to exactly the same temperature, even though they were never connected. How could that be? To answer this, physicists proposed a bold idea called cosmic inflation. Inflation suggests that in the very first tiny fraction of a second after the Big Bang, the universe expanded unbelievably fast. Not just fast, unimaginably fast. Imagine taking something smaller than a single atom and in less than a trillionth of a second, stretching it to a size much larger than a galaxy. That is, roughly the kind of growth inflation describes. To picture it in a simple way, imagine blowing up a balloon. At first, it is small. Then suddenly, in an instant, it expands to the size of a house. The surface stretches so quickly that tiny wrinkles become smooth and flat. In a similar way, inflation would have stretched the early universe so rapidly that any unevenness was flattened out. That is why distant regions look so similar today. They were once very close together before being pulled far apart. This idea solved several problems at once. It explained why space looks flat on large scales. It explained why the temperature is so uniform. It even explained how tiny fluctuations, small ripples in density, could later grow into galaxies and stars. It was elegant. But then something unexpected happened. When physicists studied the equations behind inflation more carefully, they noticed something surprising. Inflation might not stop everywhere at the same time. In some regions, it could slow down and end, allowing normal expansion and galaxy formation to begin. But in other regions, inflation might continue longer. This creates a strange picture. Instead of one single, evenly expanding universe, you might have regions where inflation stops, forming bubbles of normal space. Meanwhile, the surrounding space keeps inflating. It is like boiling water in a pot. Bubbles form in different spots. Each bubble grows and becomes its own pocket. The water around them continues to move and change. In this picture, our universe could be one of those bubbles. And if that is true, then there may be many others. This was not the original goal of inflation theory. The multiverse idea was not added on for drama. It appeared naturally from the math. That is what made it so powerful and so unsettling. Here is a gentle question. If inflation happened once, why would it only create one bubble? Why not many? If the conditions allow inflation to continue in some regions, then space could be constantly creating new bubble universes, like foam forming on the surface of the ocean. Each bubble would expand. Inside it, galaxies would form, stars would ignite, planets might appear, but the bubbles would be separated by expanding space, moving away from each other faster than light could ever travel between them. In that case, they would never meet, never communicate, never even know about each other. This is where the multiverse idea began to shift from imagination into serious physics discussion. Not because scientists wanted more universes, but because inflation, a theory created to explain our universe, seemed to suggest them. And yet, this raises a calm but important question. If these other bubbles exist, can we ever see them? The answer, at least for now, seems to be no. They would lie beyond our cosmic horizon. Even if they are real, their light would never reach us. The space between bubbles would expand too quickly. So why consider them at all? Because sometimes the structure of a theory leads somewhere unexpected. And if that theory explains many observations beautifully, you cannot ignore its deeper implications. It is like discovering that a simple map not only shows your city accurately, but also suggests the existence of distant lands beyond the borders drawn on the page. You may not have visited those lands, but if the map works so well everywhere else, you begin to wonder whether it might be pointing to something real. The birth of the multiverse idea did not come from fantasy. It came from trying to understand why our universe looks the way it does. It began with a simple problem. Why is everything so smooth? And in solving that, we may have uncovered the possibility that our universe is just one region in a much larger cosmic structure. As we move forward, we will look more closely at inflation itself, how it works, how it might create separate regions, and why some physicists believe it may still be happening somewhere, even now. For the moment, let this idea rest gently in your mind. What if the early universe did not just expand, but blossomed, and what we call our universe is just one bloom among many, floating in a vast and quiet cosmic field? Let's stay with this moment near the beginning. Not the beginning of stars, not the beginning of galaxies, but the beginning of space itself as we know it. The Big Bang is often imagined as an explosion, like a firework bursting outward into empty space. But that picture is not quite right. The Big Bang was not an explosion in space. It was the rapid expansion of space. Everything was once compressed into an incredibly hot, dense state, not packed into a point sitting somewhere, but everywhere condensed together. And then space began to stretch. At first, the expansion was already fast, but inflation suggests that for a tiny fraction of a second, it became unbelievably fast. How fast? Imagine drawing a tiny dot with a pen, smaller than the period at the end of a sentence. Now imagine that dot suddenly expanding to the size of the entire observable universe, 93 billion light-years across, almost instantly. That is the kind of expansion inflation describes. It happened in less than a blink, in less than a trillionth of a second, a time so small that if 1 second were stretched out to the age of the universe, nearly 14 billion years, that tiny inflation moment would still be shorter than a single heartbeat in that comparison. So what caused this rapid expansion? Physicists think it may have been driven by a special type of energy built into space itself. This energy would have acted like a powerful pressure pushing space outward. You can picture it like this. Imagine placing a small balloon on a table. Normally, you blow air into it to make it expand. But imagine instead that the rubber itself suddenly starts growing, stretching outward from every point at once. Inflation suggests something like that happened to space. It was not matter pushing outward into emptiness. Space itself expanded, carrying everything with it. Now here is the part that connects back to other universes. Inflation did not necessarily stop everywhere at the same time. Think about water starting to freeze. Ice forms in patches. One region solidifies first. Nearby water may still remain liquid. Gradually, more regions freeze. In a similar way, inflation may have ended in certain regions first. When it ended, normal expansion continued at a much slower rate. Matter formed. Atoms came together. Stars eventually ignited. That region became what we call a universe. But what about the areas where inflation did not stop right away? Those regions would continue expanding rapidly. And inside them, new pockets could form where inflation ended again. Each pocket would be like a bubble forming in a vast, expanding sea. If this process continued, you would not get just one universe. You would get many. Each bubble universe would be born when inflation ended locally. Inside each one, the conditions might allow matter to form, galaxies to develop, and possibly life to emerge. But the bubbles would be separated by space expanding so quickly that they could never touch. Imagine blowing soap bubbles inside a room that is itself expanding. As each bubble forms, the room grows larger at an incredible rate, pulling the bubbles farther apart. They drift away from each other faster than anything could travel between them. So here is a quiet question. Would these bubble universes all be identical? Or could they be different? At first, inflation was proposed simply to explain our universe's smoothness and flatness, but the deeper models suggest that the way inflation ends might vary slightly from place to place. If the underlying energy field that drives inflation can settle into different states, like a marble rolling into different dips on a surface, then each bubble could have slightly different properties. It is like water freezing into snowflakes. Each snowflake forms from the same basic substance, but tiny differences in conditions create unique patterns. In the same way, each bubble universe might follow similar physical laws. Perhaps the strength of gravity is slightly different. Perhaps the mass of particles changes. Perhaps the way forces behave shifts just a little. Even small differences could have huge effects. If gravity were just a bit stronger, stars might burn out quickly. If it were weaker, galaxies might never form. If the forces holding atoms together were slightly altered, chemistry as we know it might not exist. So inflation does not just stretch space, it may create diversity. But this raises something deeper. If inflation naturally produces many bubble universes, then our universe might not be special in the way we once imagined. It would be one region where inflation happened to stop in a way that allowed stars and life. Not unique, just one of many possibilities. That thought can feel unsettling, but it can also feel freeing. Instead of being the single outcome in a one-time cosmic event, our universe could be part of a much larger process, like one leaf on a vast tree. And here is another gentle question. Is inflation still happening somewhere? Some versions of the theory suggest yes. In certain models, inflation never fully stops. It continues in the background, constantly generating new bubble universes. Our bubble formed billions of years ago, but elsewhere, new ones may still be forming even now. If that is true, then reality is not a single expanding space. It is more like a growing foam, endless bubbles appearing within an ever-expanding structure. Of course, we cannot see this foam directly. It would lie beyond our observable horizon. But the idea did not come from imagination alone. It emerged from trying to solve real puzzles about the early universe. And as we continue, we will explore what it would mean if inflation truly never ended. If our universe is just one bubble, floating in an infinite, expanding cosmic sea. Let's gently continue with that image of bubbles. Imagine a pot of water sitting on a stove. At first, nothing happens. Then tiny bubbles begin to form at the bottom. They grow, rise, and pop at the surface. Now imagine something slightly different. Instead of bubbles rising and disappearing, imagine that each bubble becomes its own expanding space, and the water around them is not ordinary water, but a background that keeps expanding faster and faster. This is close to what some versions of inflation suggest. In certain models, inflation does not stop everywhere. It ends in small regions, creating bubble universes like ours. But outside those bubbles, the inflation process continues. And here is the surprising part. The space that is still inflating expands so quickly that it creates more room for new bubbles to form. Even as bubbles appear, the inflating space grows faster than they can fill it. So inflation never runs out of space to work with. It becomes eternal. Not eternal in time as we usually think of it, but ongoing without end. Somewhere, inflation is always happening. Picture a foam that keeps generating new bubbles forever. Even if some bubbles stop forming, the surrounding space grows so fast that new ones continue to appear. Our universe in this picture would be just one bubble among countless others. And because the inflating space between bubbles expands incredibly fast, faster than light could travel across it, the bubbles are permanently separated. No signal could ever cross from one bubble to another. No spacecraft, no beam of light, no message. Each bubble universe would be isolated. So here is a calm question. If they are completely separated, does it even make sense to say they are part of the same reality? It depends on how we think about it. They would all emerge from the same underlying process, the same inflating background. In that sense, they share a common origin, but they would never interact. It is like having many islands forming in a vast ocean. The ocean connects them in a broad sense, but the islands themselves never meet. Now imagine that the ocean is expanding so quickly that the islands drift apart faster than any boat could sail. From the perspective of someone on one island, the others might as well not exist. And yet, the process that formed their island continues elsewhere. This idea is called eternal inflation. It was not invented to make the universe more dramatic. It is a natural outcome of certain inflation equations. Once physicists realized this, the multiverse idea became much harder to ignore. Because if inflation is eternal, then the number of bubble universes could be enormous, perhaps infinite. That word, infinite, feels heavy. What does it mean here? If inflation continues without end and new bubbles keep forming, then there may be no upper limit to how many universes exist. Imagine a forest that grows forever. No matter how many trees you count, there are always more beyond. Or imagine a library that keeps printing new books endlessly. Every time you finish counting one shelf, new shelves appear. If reality works this way, then our universe is not the only chapter. It is one page in an ever-growing collection. But something interesting happens when you consider infinity. If there are infinitely many bubble universes, could some of them be similar to ours? Could there be another bubble with galaxies arranged in almost the same pattern? With a planet like Earth, with people asking the same questions? It feels strange, but in an infinite system, even unlikely patterns can repeat. Think of flipping a coin over and over again. If you flip it enough times, you will eventually get long streaks of heads, maybe 10 in a row, maybe 20. If you flip it endlessly, any possible sequence will appear somewhere. In the same way, if there are infinitely many universes, then every physically allowed arrangement might exist in at least one of them. But let's slow down before jumping to those deeper possibilities. There is something more basic to consider. Eternal inflation suggests that reality is much larger than our observable universe, not just larger in distance, but larger in structure. Instead of a single cosmic event, one beginning, one expansion, there may be an ongoing cosmic process. It shifts the story. The Big Bang would no longer be the absolute beginning of everything. It would be the local beginning of our bubble universe. Other bubbles might have their own beginnings at different times. Some may be older, some younger, some forming right now in distant regions we will never see. So what does that do to our sense of uniqueness? If we are one bubble among countless others, then our cosmic story is part of a much bigger narrative. It is like realizing that your hometown is one city among many on a vast planet. It does not make your city meaningless, but it places it in a broader context. There is also something peaceful about this idea. Instead of reality being a fragile one-time event, it becomes abundant, generative, creative on a scale almost impossible to imagine. But there is a challenge. If these other bubbles are forever beyond our reach, how could we ever test this idea? That question will come later. For now, just notice how the logic flows. Inflation was proposed to solve real problems in cosmology. Certain versions of inflation suggest it does not end everywhere. If it does not end everywhere, then bubble universes naturally appear. If that process continues indefinitely, we get eternal inflation. And from eternal inflation, the multiverse is not an optional add-on. It becomes a prediction. Whether that prediction reflects reality is something we are still trying to understand, but the idea itself emerged quietly, almost accidentally, from trying to explain why our universe looks smooth and flat. And as we move forward, we will explore the different ways scientists categorize these possible universes, starting with the simplest idea, that beyond our observable horizon, there may simply be more space that looks very much like ours. Let's step back for a moment. Before we imagine wildly different universes with strange laws of physics, there is a simpler idea, a quieter one. What if other universes are not different at all? What if they are simply regions of space, so far away that we can never see them? Remember the observable universe, that glowing sphere about 93 billion light-years across. That is the part of space whose light has had enough time to reach us since the beginning. But beyond that sphere, space may continue. In fact, most measurements suggest that space is either extremely large or possibly infinite. When scientists study the geometry of the universe, how space curves or bends, they find that it appears very flat on large scales. What does flat mean here? Not flat like a piece of paper. Flat in a geometric sense. If you draw two parallel lines in flat space, they never meet. On a curved surface like a globe, they eventually cross. Measurements show that on cosmic scales, space behaves almost perfectly flat. So flat that if the entire observable universe were shrunk down to the size of Earth, any curvature would be smaller than the thickness of a single sheet of paper. That suggests space may not curve back on itself in a small loop. It may stretch on and on. So here is the gentle question. If space continues forever beyond what we can see, what lies out there? Most likely, more of the same. More galaxies, more stars, more planets. But here is where it becomes interesting. If space is infinite, then the number of possible arrangements of matter within a region the size of our observable universe is actually limited. That sounds surprising. How can something be limited in an infinite space? Think about it this way. Within any large region, like our observable universe, matter can only arrange itself in so many ways. Given the laws of physics, there are only so many ways particles can be placed. Now imagine space stretching forever. If it truly is infinite, and if matter is distributed somewhat randomly, then eventually patterns would repeat. It is like writing random letters on an endless roll of paper. If the roll never ends, you would eventually see the same word appear again, maybe even the same sentence. Given enough length, entire paragraphs could repeat. In an infinite space, even rare arrangements can happen more than once. So somewhere far beyond our observable horizon, so far that light from there will never reach us, there could be a region arranged almost exactly like ours. A galaxy like the Milky Way, a solar system like ours, a planet like Earth. Perhaps even people having this same quiet conversation. That idea feels strange, but it does not require new laws of physics. It does not require strange energy fields or bubble universes. It simply requires that space continues far enough. This is sometimes called the simplest form of the multiverse. Not separate bubbles, not different physical constants, just more space beyond our cosmic horizon. It is like living inside a vast desert. You can see sand dunes in every direction, but beyond the horizon, there are more dunes. The landscape continues, even if you cannot see it. So are those distant regions separate universes? Some scientists prefer to think of them as parts of the same universe, just unobservable parts. Others call them separate universes because they are causally disconnected. That means no event in our region can ever influence them, and no event there can ever influence us. They are forever outside our light cone. Imagine two cities separated by a river so wide and flowing so fast that no bridge can ever be built and no boat can cross. Even if they share the same planet, they would never interact. In a practical sense, they would be separate worlds. Now here is another calm question. If there are infinite regions like ours, does that mean there are infinite versions of you? Possibly. If space is infinite, and if matter can only arrange itself in a finite number of ways within a region the size of our observable universe, then eventually those arrangements must repeat. The distance to the nearest exact copy would be enormous beyond imagination. Some estimates suggest it could be so far away that if you tried to travel there at the speed of light, 300,000 kilometers per second, you would need more years than there are atoms in your body. It would be so distant that the number itself becomes almost meaningless, but infinity allows repetition. Still, let's stay grounded. This idea does not say that copies are likely nearby. They would be staggeringly far away, so far that for all practical purposes, they might as well not exist. And yet, if space truly has no end, repetition becomes unavoidable. The level I multiverse, as it is sometimes described, is simply this: regions beyond our observable universe that follow the same physical laws but lie forever beyond our reach. No dramatic differences, no strange physics, just more It is the most conservative extension of what we already know. We already accept that the observable universe has a limit set by light and time. Extending space beyond that is not a radical step. It is almost modest. And yet, even this modest step changes something. It suggests that what we call the universe might be much larger than the part we see. Our cosmic bubble of visibility is about 93 billion light-years across, but the full structure may extend far beyond, possibly without end. In that case, we are not at the center. We are not near an edge. We are somewhere in the middle of a vast expanse, a region among countless others. As we move forward, we will explore more dramatic possibilities, universes with different physical constants, different rules, different outcomes. But before we leave this simpler idea, let it settle. Sometimes the most profound shift comes not from imagining something completely different, but from realizing that what we see may be only a small patch in something far, far larger than we ever expected. So far, we have explored a gentle idea. Maybe there is simply more space beyond what we can see, more galaxies, more stars, more regions following the same physical laws. But now, let's take a careful step further. What if other universes are not just far away, but fundamentally different? To understand this, we return to inflation. In some versions of inflation theory, the energy field that drove the rapid expansion of space does not settle into the same state everywhere. When inflation ends in a region, when a bubble universe forms, the underlying conditions may lock into slightly different settings. Think of it like rolling a marble across a surface, full of small dips. The marble could settle into any one of those dips. Each dip represents a different stable state. In the same way, when inflation ends, the marble of energy may settle into different valleys in different regions, and each valley could produce a universe with slightly different physical constants. Now here is the important question. What are physical constants? They are the basic numbers that shape how reality works. For example, the strength of gravity, the mass of an electron, the strength of the electromagnetic force that holds atoms together. These numbers are not chosen by us. They are built into the fabric of our universe. And here is something remarkable. If you change some of these numbers even a little, the universe would look very different. If gravity were much stronger, stars might burn through their fuel too quickly, like a candle that flares brightly and then dies in seconds. If gravity were much weaker, matter might never clump together to form stars at all. If the electromagnetic force were slightly different, atoms might not hold together in the same way. Chemistry as we know it might not exist. It is like baking a cake. If you change the amount of flour or sugar too much, the texture changes completely. A small difference can make a big impact. This leads to something called the fine-tuning problem. Why do these constants have the precise values that allow stars, planets, and life to exist? One possible answer is that there are many universes, each with different constants. Most of them might be sterile. No stars, no chemistry, no life. But in a few rare regions, the constants happen to fall into a range that allows complexity, and we find ourselves in one of those regions. It is similar to planting billions of seeds across a vast field. Most may never sprout, but a few land in just the right soil with the right sunlight and water, and they grow. In this view, our universe is not uniquely designed. It is one outcome among many. This idea is often described as a level 2 multiverse. Unlike the simpler version where distant regions follow the same laws, here different bubble universes could operate under different settings. Some might have stronger gravity, some weaker, some might have different types of particles, some might not allow stable matter at all. Now pause for a moment. If that is true, could there be universes where stars shine blue instead of yellow, where chemistry forms substances we cannot imagine, where time flows differently? Possibly. But there are limits. The underlying structure may still follow certain mathematical rules. It would not be pure chaos. Rather, it would be variation within a broader framework. Think of musical instruments. A piano has fixed keys, but you can play endless melodies by pressing different combinations. The structure remains the same, but the outcomes vary. In the same way, the deeper laws of physics may allow different melodies of reality, depending on how certain values settle. Now here is a gentle question. If most universes are uninhabitable, how do we explain our own? This is where the anthropic idea enters quietly. We observe this universe because it allows observers. If the constants were wrong for life, there would be no one there to notice. It is like fish asking why the ocean has water. They exist because the water allows them to exist. But is that explanation satisfying? Some people feel it sounds like avoiding a deeper answer. Others see it as a natural consequence of a multiverse. If there are countless universes with different constants, then it is not surprising that at least one would have the right balance. It would be surprising only if there were just one universe and it happened to be perfectly tuned. The level 2 multiverse is more dramatic than the first level. It suggests not just distant copies, but entirely different cosmic settings. And yet, like eternal inflation, it arises from attempts to explain real observations. It is not fantasy added for excitement. It grows from the mathematics of inflation and fields. But here is the quiet challenge. If these other bubble universes are forever separated from us by expanding space, how could we ever test whether their constants are different? For now, we cannot. The idea remains theoretical. Still, it reshapes the question. Instead of asking, why is our universe fine-tuned? We might ask, why wouldn't at least one universe in a vast multiverse be fine-tuned? It shifts the sense of rarity. Our universe could be like one lucky combination on an enormous cosmic lock. If you spin the dial enough times across countless universes, eventually the right numbers align. As we continue, we will explore an even stranger possibility, one that does not arise from cosmic expansion, but from the strange behavior of particles at the smallest scales. Because the multiverse idea does not live only in the vastness of space. It may also hide in the quiet world of quantum mechanics, where reality itself seems to branch in ways that challenge common sense. So far, our journey through possible universes has taken place in the vastness of space, beyond the horizon, beyond distant galaxies, beyond expanding cosmic bubbles. But now, we turn inward, not inward in distance, but inward in scale, down to the smallest levels of reality. To understand this next idea, we need to talk about something that already feels strange on its own. Quantum mechanics. Quantum mechanics is the set of rules that describe how particles behave at very small scales, smaller than atoms, smaller than anything we can see directly. And the first thing you notice about quantum behavior is that it does not act like everyday objects. If you throw a ball, you can track its path. You can predict where it will land. It moves along a clear trajectory, but a tiny particle, like an electron, does not behave that way. Instead of being in one specific place, it can exist in a spread of possibilities at once. Scientists describe this using something called a wave function, which represents different possible outcomes. Now here is where it becomes interesting. When you measure the particle, when you observe it, you do not see all possibilities. You see one result. For example, imagine a particle that could go left or right. According to quantum mechanics, before you measure it, it exists in a kind of blend of both possibilities. But when you measure it, you see it go either left or right. So what happened to the other possibility? For many years, the common explanation was that the wave function collapses. The act of measurement forces one outcome to become real, and the others disappear. But in the 1950s, a physicist named Hugh Everett suggested a different idea. What if the wave function never collapses? What if all possibilities continue? but in separate branches. In this picture, when the particle faces two possible outcomes, the universe splits into two branches. In one branch, the particle goes left. In the other, it goes right. Both outcomes happen, but in different versions of reality. Imagine standing at a fork in the road. One path goes into a forest, the other leads to a lake. In everyday life, you choose one path. But in this interpretation of quantum mechanics, both choices occur, each in its own branch of reality. And here is the surprising part. This branching does not happen just for big decisions. It happens constantly, at the level of tiny particles. Every time a quantum event has multiple possible outcomes, reality branches. That would mean the universe is not a single unfolding story. It is a constantly branching tree. With each moment, the number of branches multiplies. To picture this, imagine a tree where every leaf splits into two new leaves every second. After 1 second, you have twice as many leaves. After 2 seconds, 4 times as many. After 3 seconds, 8 times. Very quickly, the number becomes enormous. If branching happens at the quantum level, it could occur countless times every second. The number of parallel histories would grow beyond imagination. Now here is the quiet question. Where are these other branches? They are not far away in space. They do not require vast cosmic distances. Instead, they exist alongside us, but in separate, non-communicating branches of reality. Think of it like radio channels. Right now, many signals may be passing through the room you are in. Music, conversations, broadcasts. But your radio only tunes into one frequency at a time. The others are there, but you cannot hear them. In the same way, each branch of reality follows its own path. We experience one branch, the others unfold separately, and they do not interact. So what does this mean for you? If every possible quantum outcome branches, then every possible version of your life, within the limits of physics, may unfold in some branch. In one branch, you made one choice, in another, a different one. But it is important to stay calm here. These are not magical fantasy versions of you making impossible decisions. The branching follows the rules of physics. It is not about unlimited imagination. It is about physical possibilities. Still, the idea feels profound. Instead of a single line of time, reality becomes a vast web of parallel histories. This interpretation is often called the many worlds interpretation of quantum mechanics. And unlike some multiverse ideas, it does not require new physics beyond standard quantum theory. It simply takes the equation seriously and removes the idea of collapse. Now here is a natural question. If these branches exist, why can we not detect them? Because once they separate, they no longer interfere with each other. The mathematics shows that branches quickly become independent. It is like two ripples on a pond that move in different directions and never cross again. From our perspective inside one branch, the others are invisible. So does this count as a multiverse? In one sense, yes, but it is not multiple universes separated by distance. It is multiple realities separated by quantum branching, and it changes how we think about possibility. Instead of asking, what might have happened, we might say, what might have happened did happen, just not in this branch. It is a subtle shift. As we continue, we will explore an even more radical idea, one that suggests that every consistent mathematical structure might exist physically somewhere. But for now, let this idea settle gently. The multiverse may not only stretch outward into distant space, it may also unfold quietly at every moment, branching in ways we never see, yet always part of the deeper structure of reality. We have slowly expanded our view. First, we imagined more space beyond our horizon, then different bubble universes with different physical constants, then branching realities emerging from quantum events. Now we arrive at perhaps the most radical idea of all, What if every possible mathematical structure exists physically? Not just different settings of the same laws, not just branches of the same universe, but entirely different kinds of realities, built from different mathematical rules altogether. To approach this gently, let's begin with something simple. Physics, at its core, is written in mathematics. When scientists describe gravity, they use equations. When they describe particles, fields, and forces, they rely on numbers and symbols. The deeper we go into understanding the universe, the more it seems that reality follows mathematical patterns. The motion of planets follows precise formulas. The behavior of light can be written in equations. Even the expansion of space can be described with mathematical expressions. It is almost as if the universe is not just described by math, but is math. Now here is a quiet question. Is mathematics something we invented or something we discovered? If you imagine a triangle, 3 straight lines meeting at 3 corners, the angles always add up to the same total in flat space. That fact was true long before humans existed. We did not create it, we uncovered it. In that sense, mathematics feels like a landscape waiting to be explored. There are simple structures, like addition and multiplication. There are more complex ones, like geometry and algebra. And then there are vast abstract systems, higher dimensions, strange symmetries, different logical frameworks. Many of these mathematical structures are consistent. They do not contradict themselves. They follow clear internal rules. So here is the bold idea. If our universe exists because it is a consistent mathematical structure, why should only one such structure exist physically? Why not all of them? Imagine a library containing every possible book that can be written using a fixed alphabet. Most of those books would be nonsense, but some would contain meaningful stories. Now imagine that instead of books, we are talking about mathematical systems. Each consistent system defines a possible reality. In one system, space might have 3 dimensions. In another, it might have 4 or 10. In one, gravity behaves the way we know it. In another, there might be entirely different forces. Each mathematical structure would correspond to a different kind of universe. This idea suggests that physical existence and mathematical existence are the same thing. If a structure is mathematically consistent, then somewhere, in some sense, it exists physically. That is a deeply radical thought. It means reality is not limited to variations of our own laws. It means every logically possible framework could be real. Now pause for a moment. What would that mean for us? It would mean our universe is not just one bubble among many, with slightly different constants. It is one mathematical structure among an unimaginable landscape of structures. Think of it like shapes. There are circles, squares, triangles, spirals. Each follows its own rules. Each has its own properties. Now imagine that instead of shapes on paper, each shape is a full universe. In one universe, time might flow differently. In another, space might not behave in ways we recognize. In some, complexity may never arise. In others, forms of life may exist that we cannot even picture. It stretches the mind, but here is the gentle challenge. How could we ever test such an idea? Unlike inflation or quantum branching, which arise from physical theories we can examine, this idea goes even deeper. It moves into the foundations of why reality exists at all. It asks, why this set of equations and not another? If all mathematical structures exist, then there is no need to explain why our universe has these laws. It has these laws because we exist in this particular structure. Observers can only arise in certain types of mathematical systems. It becomes a kind of ultimate extension of the anthropic idea. We observe this universe because this is one of the structures that allows observers. But does that feel satisfying? Some find it elegant, others find it unsettling. Because if all possible mathematical structures exist, then uniqueness becomes difficult to define. there could be universes completely unlike ours, universes with no resemblance to space, matter, or time as we know them, universes where entirely different forms of logic apply, and yet all equally real within their own frameworks. It is like imagining that reality is not a single painting, but an entire gallery containing every painting that could ever be consistently drawn. We inhabit one canvas, the others hang in a vast abstract space we cannot access. This idea pushes the multiverse to its furthest edge. It is no longer about distant space, or branching timelines, or bubble universes. It is about the nature of existence itself. Is reality special, or is it one expression within a boundless mathematical landscape? For now, this remains a philosophical extension of physics. It does not come with clear experimental predictions, but it does something powerful. It forces us to confront the possibility that reality may be far more varied than we can imagine. And as we continue, we will return to a more grounded puzzle, the question of fine-tuning. Because whether or not all mathematical structures exist, we still face a striking fact. The constants of our universe seem precisely balanced in a way that allows stars, chemistry, and life. And that mystery will guide our next step. Let's return to something simple. Look around you. Solid ground beneath your feet, air you can breathe, light from a star 150 million kilometers away, warming the surface of a small planet. None of this feels fragile. It feels normal, stable, reliable. And yet, when physicists examine the basic numbers that shape our universe, they notice something surprising. The laws of physics depend on certain constants, fixed values that determine how strong forces are, how heavy particles are, and how quickly space expands. These numbers are not chosen by us, they are simply there. But if you change some of them even slightly, the universe would look completely different. Let's take gravity. Gravity is the force that pulls matter together. It allows gas clouds to collapse into stars. It keeps planets in orbit. It holds you to the surface of Earth. If gravity were much stronger, even a small increase, stars would burn through their fuel much faster. Imagine turning up the flame on a stove too high. The water boils away quickly. In a similar way, stars might live short, intense lives, lasting millions of years instead of billions. That might not leave enough time for life to slowly evolve. If gravity were much weaker, matter might never clump together at all. Gas would drift apart. Stars might never ignite. The universe would remain dark and diffuse, like smoke spreading thinly in the air. Now think about the electromagnetic force. This force holds electrons in orbit around atomic nuclei. It allows atoms to form molecules. It allows chemistry, and chemistry allows life. If this force were slightly stronger, atoms might bind too tightly. Chemical reactions could become rigid and limited. If it were weaker, atoms might not hold together properly at all. It is like adjusting the strings on a guitar. If they are too tight, they snap. If too loose, they cannot produce clear notes. There is a narrow range where music can exist. Many constants in physics seem to sit within narrow ranges that allow complexity. Another example is the expansion rate of the universe. Right after the Big Bang, space began expanding. If that expansion had been much faster, matter would have spread out too quickly for gravity to pull it into galaxies. If it had been much slower, gravity might have caused the universe to collapse back in on itself long before stars formed. It is like tossing a ball upward. Throw it too gently, and it falls back immediately. Throw it too hard, and it escapes completely. There is a range where it rises, slows, and allows interesting motion. So here is the quiet question. Why do these constants have the values they do? Why not slightly different ones that would make life impossible? Some physicists see this as a deep mystery. It feels as though the universe is fine-tuned, balanced with remarkable precision, but we must be careful with that phrase. Fine-tuned does not necessarily mean designed. It simply means that small changes would lead to very different outcomes. Now imagine a vast control panel with many dials. Each dial represents a physical constant. If you turn a dial too far in either direction, stars vanish, atoms fail, or structure never forms. Our universe seems to sit in a region where the dials are set just right for complexity. That observation leads to several possible explanations. One possibility is that there is a deeper physical law we do not yet understand, one that forces these constants to have the values they do. In this view, they are not adjustable at all. They could not have been different. Another possibility connects back to the multiverse. If there are many universes, each with different constants, then most would be lifeless. But in a few rare ones, the constants would fall into the narrow, life-friendly range. We find ourselves in one of those. It is like walking into a vast desert with millions of empty patches of land. Most are dry and barren, but here and there you find an oasis. You happen to be standing in one of those oases, not because the desert was designed for you, but because only in the oasis could you survive long enough to ask the question. This shifts the perspective. Instead of asking, why is the universe tuned for life? We ask, given many universes, where could observers exist? But does this solve the problem, or simply move it? If the multiverse exists, and constants vary across different universes, then fine-tuning may not require a special explanation. It becomes a selection effect. We observe this universe because we could not exist in most others. Yet some people feel this answer lacks depth. They wonder whether invoking many unseen universes is more complicated than searching for a deeper underlying law. So the fine-tuning problem sits at the crossroads. It connects cosmology, particle physics, and philosophy. It forces us to ask not just how the universe works, but why it has the particular structure it does. And it gently pushes us toward the next idea. If we only observe universes that allow observers, then our perspective is not random, it is filtered. This leads to something called the anthropic principle, the idea that our existence shapes what kind of universe we can observe. As we move forward, we will explore whether that idea feels satisfying or whether it raises new questions of its own. For now, let this settle quietly. The constants of nature sit in a delicate range, not balanced like a fragile glass ready to shatter, but positioned in a way that allows stars to shine for billions of years, planets to cool, chemistry to unfold, and life to slowly emerge. Whether that balance is unique, inevitable, or one example among countless possibilities, remains one of the most profound questions in our search for other universes. Let's stay with the feeling of fine-tuning for a moment. The constants of nature seem to sit in a narrow range that allows stars, planets, chemistry, and eventually life. That observation leads to a quiet but powerful idea. We observe this kind of universe because only this kind of universe allows observers. This is often called the anthropic principle. The word anthropic simply relates to human beings, but the idea applies to any form of observer, not just us. It says that the universe we see must be compatible with our existence, because if it were not, we would not be here to notice it. At first, this sounds almost too simple. Of course, we live in a universe that allows life. If it did not, we would not exist. But the deeper question is whether this explanation is enough. To understand it gently, imagine a large lottery with billions of tickets. Most tickets lose. A tiny number win. Now imagine you are holding a winning ticket. You might ask, why did I win? One answer is, because you happened to hold the winning number. Out of all possible tickets, someone had to win. You just happened to be that person. From your perspective, it feels special. But from the perspective of the entire lottery, it was inevitable that someone would win. The anthropic idea suggests that the universe may be similar. If there are many universes with different constants, then most would not allow life, but a few would, and observers would only ever find themselves in those few. So from inside such a universe, it would appear fine-tuned. But is that satisfying? Some people find it elegant. It removes the need to assume design or hidden purpose. It simply says, given enough variation, some regions will naturally allow complexity. Others feel it avoids a deeper explanation. They ask, why is there a multiverse in the first place? Why are the constants allowed to vary? Why does the larger structure have the capacity to produce life-friendly regions? The anthropic principle does not answer those questions. It shifts the focus. It reminds us that our perspective is filtered by our own existence. Here is a simple example. Imagine a fish asking why the ocean contains water. The fish may think water is a special feature designed for it, but from a broader view, fish exist because water exists. They evolved in that environment. If the ocean were made of sand instead, fish would not be there to ask the question. In the same way, we exist because the universe allows life. If it did not, there would be no observers. But here is a deeper layer. Some constants in physics seem to be extremely sensitive. Even small changes might prevent structure from forming. That narrow range feels striking. Is it simply a coincidence? Or is it evidence of many trials across a multiverse? Imagine a safe with many dials. Each dial must be set within a narrow range for the safe to open. If you try once and succeed, it feels remarkable. But if you spin the dials billions of times, success becomes more likely somewhere. In a single universe picture, the dials were set once. In a multiverse picture, the dials are set many times across different regions. We find ourselves in a region where the combination works. Still, some physicists prefer to search for deeper laws. They suspect that the constants may not be free to vary. Perhaps they are fixed by underlying principles we have not yet discovered. History gives us reason to be cautious. In the past, certain values in physics seemed arbitrary. Later, deeper theories explained why they had to be that way. So here is the calm question. Is the anthropic principle a final explanation, or a temporary placeholder? It may depend on whether future discoveries reveal hidden connections between constants. There is also a philosophical layer. If many universes exist with different constants, then our universe is not uniquely privileged. It is one environment among many. That can feel humbling, but it can also feel liberating. It suggests that reality may be vast enough to explore every possibility allowed by physics, and life emerges where it can. The anthropic principle does not claim that the universe was made for us. It suggests that we are shaped by the universe we happen to inhabit. Like plants growing towards sunlight, we adapt to the conditions available. Still, there is something deeply human about asking why the constants are what they are. We want to know whether there is a deeper reason, and that desire continues to drive research in fundamental physics. As we move forward, we will explore how certain advanced theories, especially those involving tiny vibrating strings and extra dimensions, suggest that there may be an enormous number of possible vacuum states, each corresponding to different physical constants. If that is true, the multiverse may not be a philosophical idea at all. It may be a natural outcome of deeper mathematical structures. For now, let the anthropic principle rest gently. It reminds us that observation is not neutral. We see a universe compatible with our existence, because only such a universe can host observers. Whether that is the full story or just one piece of a much larger puzzle is something we will continue to explore. Let's gently step deeper into the foundations of physics. For many years, scientists have searched for a single framework that unites all the forces of nature: gravity, electromagnetism, and the forces that operate inside atoms. One of the most ambitious attempts to do this is called string theory. The basic idea is surprisingly simple, even if the mathematics behind it is complex. Instead of imagining the smallest particles, like electrons and quarks, as tiny point-like dots, string theory suggests they are incredibly small vibrating strings, not strings like shoelaces, not even strings you could see with the most powerful microscope. These would be smaller than atoms by an unimaginable amount. To give you a sense of scale, an atom is about 1/10,000,000th of a millimeter wide. If an atom were enlarged to the size of our solar system, a string would still be smaller than a tree. These strings would vibrate in different ways, and each pattern of vibration would correspond to a different particle. It is a little like a violin. When you pluck a string, the vibration creates a specific note. Change the vibration, and you change the note. In string theory, the notes are particles. The way the string vibrates determines whether it appears as an electron, a photon, or another particle. This idea is elegant. It suggests that all particles are variations of the same fundamental object. But here is where things become even more interesting. For string theory to work mathematically, it requires more dimensions than the 3 dimensions of space we experience, plus time. In most versions, it requires 10 dimensions in total. So where are the extra dimensions? The theory suggests they are compactified, curled up so tightly that we cannot see them. Imagine a garden hose lying on the ground. From far away, it looks like a one-dimensional line. But if you zoom in closely, you see that it has a circular dimension around it. In the same way, space might have extra dimensions curled up at extremely small scales. Now here is the key connection to the multiverse. The shape and size of these curled up dimensions affect how strings vibrate. And the way strings vibrate determines the properties of particles and forces. Different shapes of these extra dimensions could lead to different physical constants. Think of it like tuning an instrument. If you change the shape of a violin's body, the sound changes. In string theory, if the extra dimensions are shaped differently, the music of the universe, the particles and forces, changes. And here is the surprising part. There may be an enormous number of possible shapes for these extra dimensions. Not just a few, not dozens, but possibly an almost unimaginable number, sometimes estimated to be as large as 10 to the power of 500. That number is difficult to picture. 10 to the power of 500 means a 1, followed by 500 zeros. For comparison, the number of atoms in the observable universe is estimated to be around 10 to the power of 80, a 1 followed by 80 zeros, so 10 to the power of 500 is vastly larger. It is like comparing a single grain of sand to all the grains on every beach on Earth, and then repeating that comparison again and again. Each possible shape of the extra dimensions corresponds to a different vacuum state, a different set of physical constants. This collection of possibilities is often called the string landscape. Imagine standing on a vast mountain range with countless valleys. Each valley represents a different stable configuration of extra dimensions. When the universe settles into one valley, it locks in a specific set of constants. In the context of inflation, different bubble universes might settle into different valleys in this landscape. So string theory does not just allow multiple universes. It almost expects them. If there are many possible stable configurations, and inflation creates many bubble universes, then different bubbles could land in different valleys of the landscape. Each bubble would have its own version of physics. Some might resemble ours. Others might differ slightly. Many might be completely unsuitable for complex structures. Now pause for a moment. This means the constants of our universe might not be uniquely determined by deep necessity. They might be one choice among an enormous menu of possibilities. We find ourselves in a universe where the constants allow stars, chemistry, and life. Perhaps because only such valleys in the landscape allow observers. Once again, the anthropic idea appears, but there is also a challenge. String theory, despite its mathematical beauty, has not yet produced direct experimental evidence. The scales at which strings would be detectable are far beyond what our current technology can probe. So the landscape remains a theoretical framework. Still, it offers a possible explanation for why the constants of nature might vary across different universes. It connects the fine-tuning problem with a deeper mathematical structure. Instead of asking why the constants have their specific values, we might ask why our bubble universe settled into this particular valley in a vast landscape. And if the landscape is real, then the multiverse may not be optional. It may be the natural outcome of a theory trying to unify all forces. As we continue, we will explore how the idea of extra dimensions, already present in string theory, opens the door to even more surprising possibilities. Because if extra dimensions exist, other universes might not just be far away. They might exist alongside us, hidden in dimensions we cannot directly perceive. Let's stay with the idea of extra dimensions for a while. It sounds like something from science fiction, but in modern physics, extra dimensions appear not as decoration, but as a mathematical requirement in certain theories. We experience 3 dimensions of space, left and right, forward and backward, up and down. And then there is time flowing steadily forward. That makes 4 dimensions we directly notice, but some theories suggest there may be more. The natural question is simple. If extra dimensions exist, why don't we see them? To understand this gently, imagine walking on a tightrope stretched between 2 buildings. From far away, the rope looks like a simple line. You can only move forward or backward along it. But if you were an ant crawling on that rope, you would notice something different. The rope has thickness. You could walk around its circular surface as well as along its length. To a distant observer, the rope seems one-dimensional, but up close, it has more structure. In a similar way, extra dimensions might be curled up so tightly that we cannot perceive them at everyday scales. They could exist at lengths far smaller than atoms. To picture that scale, imagine shrinking a single atom until it is the size of a basketball. A curled up extra dimension might still be smaller than a grain of dust in comparison. They would be hidden not because they are far away, but because they are extremely small. Now, here is where things become interesting for the multiverse idea. If extra dimensions exist, our universe might be like a sheet, sometimes called a brain, floating within a higher dimensional space. Imagine a flat piece of paper floating in a larger room. Creatures living on the paper would experience only 2 dimensions, forward/backward and left/right. They would have no direct awareness of the up/down direction outside their sheet. In some models, our 3-dimensional space could be like that sheet. Other sheets, other brains, could exist nearby in the higher dimensional space. They might be separated from us by a tiny distance in an extra dimension, but because we are confined to our own brain, we cannot move into that direction. It would be like being trapped on the surface of the paper. This raises a calm but fascinating question. Could there be other universes just next to ours, separated by a small distance, in a dimension we cannot access, not billions of light years away, not beyond our observable horizon, but right beside us, in a higher dimensional sense? Some models even suggest that gravity may leak slightly into extra dimensions. This could explain why gravity is so much weaker than the other forces. Think about it like this. If you pour water onto a flat table, it spreads out across the surface. But if the table has hidden cracks or channels beneath it, some water may flow away into those unseen spaces. In a similar way, gravity might spread into extra dimensions, making it appear weaker within our own. While this idea remains speculative, it shows how extra dimensions could have real physical consequences. Now imagine that there are other brains in this higher dimensional space. Each brain could host its own universe, its own stars, its own particles, its own physical constants. And because we are confined to our brain, we would never directly see or visit the others. It would be like two sheets of paper stacked very close together but never touching. The creatures on one sheet would be unaware of the other. This picture is sometimes described as a brand world scenario. It feels less like distant bubbles and more like parallel layers. But here is the gentle challenge. How could we test whether extra dimensions exist? Physicists have searched for signs. For example, they look for tiny deviations in gravity at very small distances. If gravity behaves differently than expected at sub-millimeter scales, about the thickness of a coin, that might hint at extra dimensions. So far, experiments have not confirmed such deviations, but the search continues. Extra dimensions also appear naturally in string theory, where they shape how strings vibrate and determine physical constants. So even if we cannot see them directly, they may still influence the structure of our universe. And if they are real, the multiverse may not only stretch outward into distant space, it may also extend sideways into hidden directions. Now pause and imagine this. You are sitting quietly in a room. Around you, in directions you cannot perceive, there may be entire worlds existing in dimensions beyond your senses, not interacting, not colliding, just coexisting. It is a subtle and peaceful thought. Reality might be layered, and we experience one layer. As we continue, we will explore an even more dramatic possibility connected to these extra dimensions. The idea that universes might form when higher dimensional brains collide. If that is true, then our Big Bang might not have been the absolute beginning, but the result of a cosmic interaction in a larger, hidden space. Let's gently continue with the image of sheets floating in a higher dimensional space. If our universe is like a three-dimensional surface, a brain existing inside a larger space with extra dimensions, then something interesting becomes possible. What if these brains can move? And if they move, what happens when they meet? In some versions of string-inspired cosmology, our universe may have begun when two higher dimensional brains collided, not a collision like two cars crashing on a highway, more like two vast cosmic sheets drifting through a higher dimensional space, eventually brushing against each other. To picture this, imagine two enormous transparent curtains floating in a large room. They are almost weightless, gently drifting. At some point, they touch. At the moment of contact, energy is released across their surfaces. In the brain collision idea, that release of energy could appear from inside one of the brains as a Big Bang. In other words, what we call the beginning of our universe might not have been the beginning of everything. It might have been the moment our brain collided with another. Now pause for a moment. From inside our universe, the Big Bang looks like the start of space and time. When we trace the expansion backward, we find everything compressed into an extremely hot, dense state. But if our universe is embedded in a larger structure, then that hot beginning could be the result of a higher dimensional event. The collision would inject enormous energy into our brain. How enormous? Think about the total energy contained in all the stars of the observable universe, billions upon billions of galaxies, each with billions of stars. The energy released in the first moments after the Big Bang would have been greater than all of that combined. It would be like compressing the energy of countless suns into a region smaller than a grain of sand. The temperatures would have been unimaginable. Trillions upon trillions of degrees, far hotter than the core of any star. For comparison, the center of our sun is about 15 million degrees Celsius. The early universe was hotter by a factor so large it becomes difficult to express in everyday numbers. And yet, if this energy came from a brain collision, then outside our brain, the larger, higher dimensional space may have remained relatively calm. The dramatic explosion we see from inside could be just a ripple in a larger reality. This idea is sometimes connected to what is called the ekpyrotic or cyclic model, where brains periodically move toward each other, collide, and then separate again. If that is true, our universe could be one phase in an ongoing cycle of collisions. Imagine two pendulums swinging slowly in a vast room. They drift toward each other, touch, release energy, and then swing apart again. After an extremely long time, they drift back and collide once more. Each collision could give birth to a new, hot, expanding universe. Now here is the quiet question. If this is true, could there be other brains out there right now? Possibly. The higher dimensional space, sometimes called the bulk, could contain many brains, each hosting its own universe. Some may have already collided, some may never collide, some may be drifting in different directions entirely. From inside our brain, we would not directly see these others, just as a character in a two-dimensional world could not see objects floating above their surface. But the mathematics allows for this picture, and it offers a fascinating shift. The Big Bang becomes not an absolute beginning, but an interaction. Instead of something from nothing, it becomes something from contact. That can feel less mysterious in some ways, but it also raises new questions. What drives the motion of brains? Why do they exist at all? Is the higher dimensional space infinite? Does it have its own structure and rules? These are questions still being explored. The brain collision theory remains speculative. It has not been confirmed by direct evidence. However, physicists have searched for possible signatures. For example, certain patterns in the cosmic microwave background, the faint afterglow of the early universe, might carry hints of unusual beginnings. So far, observations have not clearly pointed to a brain collision, but the data does not completely rule it out either, and the idea remains part of the broader landscape of multiverse possibilities. What makes this picture unique is that it does not rely only on distant bubbles or branching timelines. It suggests our universe is one layer in a higher dimensional structure. The multiverse, in this case, is not infinitely far away. It is just separated by directions we cannot travel. Now imagine this quietly. Beyond the space we see, beyond the galaxies and cosmic expansion, there may be an unseen dimension where vast brains drift slowly, like calm ships on an endless sea. Occasionally they meet, and when they do, a universe ignites. Stars eventually form, planets cool, life arises, questions are asked, and inside one of those brains, beings look up at the night sky and wonder how it all began. As we move forward, we will ask whether universes could ever collide in ways we might detect, and whether our cosmic history might contain faint clues of such encounters. For now, let the idea rest. The beginning of our universe may not have been a solitary event. It may have been the echo of a deeper, higher dimensional meeting in a reality far larger than we can see. If our universe is one bubble among many, or one brain among others, then a natural question quietly appears. Could universes ever collide? Not in a dramatic, explosive way that destroys everything, but in a subtle way that leaves traces. To explore this, let's return to the bubble picture from Eternal Inflation. Imagine a vast, ever-expanding space where bubble universes form like pockets in foam. Each bubble expands. Inside each one, galaxies form. Light travels. Time unfolds. Now imagine two bubbles forming near each other. As they expand, their surfaces might eventually meet. What would that look like? From inside one bubble, from inside a universe like ours, it would not appear as a giant external object crashing into us. We would not see a wall approaching in the sky. Instead, the collision would show up as a disturbance in the structure of space itself. Think about dropping two stones into a calm pond. Each stone creates ripples. If the ripples overlap, they create patterns, rings intersecting, waves interfering. In a similar way, if two bubble universes collided early in their history, the interaction might leave faint patterns imprinted on the fabric of space. But here is the important detail. Such a collision, if it happened, would most likely have occurred very early, when our universe was still extremely young and hot. Why early? Because as the universe expands, regions move farther apart. If two bubbles were going to meet, it would probably happen soon after they formed. Now imagine this. The universe is only a tiny fraction of a second old. It is filled with hot, dense energy, and somewhere along its expanding boundary, it brushes against another bubble universe. The collision would create a disturbance, a region where energy is slightly different. That disturbance would spread inward at the speed of light. Over billions of years, as the universe cools and expands, that early disturbance could leave a subtle mark in the cosmic microwave background. The cosmic microwave background, or CMB, is the faint afterglow of the early universe. It is like a snapshot taken when the universe was about 380,000 years old, very young compared to its current age of nearly 14 billion years. To put that in perspective, if the age of the universe were compressed into a single year, 380,000 years would be just a few minutes after midnight on January 1st. The CMB carries tiny temperature variations, differences as small as 1 part in 100,000. That is like measuring temperature changes, smaller than a drop of water, in an Olympic swimming pool. Physicists have carefully mapped these variations using satellites. So here is the question. Could any unusual patterns in that map be evidence of a past collision with another universe? Researchers have searched for circular patterns, regions slightly warmer or cooler than expected, that might hint at such an event. It is like scanning a calm lake for faint ripples that do not fit the usual pattern. So far, no clear confirmed evidence of a bubble collision has been found. There have been a few hints. Some analyses have suggested possible circular features, but when studied more closely, they have not provided strong enough proof. The data remains consistent with the simpler explanation: random fluctuations from the early universe. Still, the search continues. And here is something important. Even if bubble collisions are possible in theory, they may be extremely rare, or the conditions required for a detectable collision may be unlikely. It is also possible that our observable universe lies far from the boundary of our bubble. If the collision happened beyond our visible region, we would never know. Remember, our observable universe is about 93 billion light-years across, but the full bubble, if it exists, could be far larger. So even if a collision occurred somewhere in our bubble, its signal might lie forever beyond our horizon. This brings us back to a quiet theme. There may be things happening in the larger structure of reality that we can never observe directly, but we can look for subtle clues. Physicists also consider whether collisions could affect large-scale structure, the way galaxies are distributed, or create slight asymmetries in the expansion of space. So far, our universe appears remarkably uniform, but that uniformity itself is part of what makes the search delicate. The patterns are faint, and distinguishing them from random fluctuations is challenging. Now pause and consider something deeper. If a collision were ever confirmed, what would that mean? It would mean our universe is not alone, not as an abstract idea, not as a mathematical possibility, but as a physical neighbor. It would mean that beyond our cosmic boundary, other bubble universes exist, and at least once, they touched. That would transform the multiverse from speculation into observation. But until such evidence appears, the idea remains open, possible, intriguing, unconfirmed. Still, the fact that we can even ask this question is remarkable. We are tiny beings on a small planet, orbiting an average star in a galaxy among billions, and yet we can imagine and search for traces of interactions between entire universes. As we continue, we will look more closely at the cosmic microwave background itself, what it reveals about the early universe, and how its precise measurements shape our understanding of whether other universes might exist. For now, let this thought rest gently. If other universes are out there, they may not remain forever silent. They might leave whispers, etched faintly into the oldest light in the sky. Let's turn our attention to that oldest light, the cosmic microwave background. If you could see it with your eyes, the entire sky would glow faintly in every direction, not bright like the sun, not even visible in normal light, but in microwave wavelengths, invisible to us. There is a soft, uniform glow filling all of space. This light is ancient. It began when the universe was about 380,000 years old. That may sound like a long time, but compared to the universe's current age of nearly 14 billion years, it is incredibly early. Imagine compressing the entire history of the universe into one single year. On that scale, the cosmic microwave background would appear on January 1st, just minutes after midnight. It is the earliest light we can see. Before that time, the universe was so hot and dense that light could not travel freely. It was like trying to see through thick fog. Photons, particles of light, kept bouncing off charged particles. But as the universe expanded, it cooled. Eventually, it cooled enough for electrons and protons to combine into neutral atoms. When that happened, light was finally able to travel without constantly scattering. That light has been traveling ever since. For nearly 14 billion years, it has crossed expanding space, stretching along the way. Originally, it was visible light, glowing intensely, but as space expanded, its wavelength stretched. Now it sits in the microwave part of the spectrum, and it is remarkably uniform. In every direction, its temperature is about 2.7 degrees above absolute zero. Extremely cold. Absolute zero is the coldest temperature possible, about minus 273 degrees Celsius. So 2.7 degrees above that is still far colder than anything naturally found on Earth. If you could compare it to a household freezer, which might sit around minus 18 degrees Celsius, the cosmic microwave background is far colder than the emptiest Antarctic winter. But here is where it becomes fascinating. Although it is uniform, it is not perfectly uniform. There are tiny fluctuations, differences in temperature of about 1 part in 100,000. To picture that, imagine measuring the height of Mount Everest, about 8,800 meters tall, and noticing a bump only 8 centimeters high at the peak. That is the level of variation we are talking about. These tiny fluctuations are incredibly important. They are the seeds from which galaxies grew. In the early universe, regions that were slightly denser than average pulled in more matter through gravity. Over billions of years, those small ripples turned into the vast web of galaxies we see today. But the cosmic microwave background does more than show us structure formation. It gives us clues about the shape and composition of the universe. By mapping the tiny temperature variations across the sky, scientists can test models of inflation. They can measure how flat space is. They can estimate the amount of dark matter and dark energy. Several missions have studied the CMB in detail, including satellites that orbited far from Earth to avoid interference. These instruments measured temperature differences as small as millionths of a degree. It is like detecting a change in temperature smaller than the warmth of a single breath in a large room. The data has confirmed many predictions of inflation. The universe appears very flat. The fluctuations match patterns expected from rapid early expansion. The large-scale structure aligns with these early seeds. So what about other universes? If our universe collided with another bubble long ago, or if unusual early conditions existed, they might leave unusual patterns in the CMB. Researchers have searched for anomalies, circular cold or hot spots, unusual alignments, patterns that seem too large or too symmetric to arise from random fluctuations. There are a few features in the CMB that continue to be studied. For example, there is a region sometimes called the cold spot, an area slightly cooler than average, spanning about 5 degrees across the sky. to picture that, hold your hand at arm's length. The width of 3 fingers side by side is roughly 5 degrees of the sky. Some have wondered whether this feature could be a sign of a past collision with another universe. However, most studies suggest it can be explained by normal cosmic structure, perhaps a large region with fewer galaxies. So far, no pattern has provided strong, undeniable evidence of other universes. But the CMB remains one of our best tools. It is like a photograph of the universe as a newborn. If anything unusual happened in those earliest moments, it might be recorded there. And yet, we must be careful. When you look at clouds, you sometimes see shapes, faces, animals, patterns. The human mind is good at finding structure, even in randomness. Scientists use careful statistical analysis to avoid being misled by patterns that appear significant, but are actually expected in random data. The cosmic microwave background has been measured with incredible precision, and so far it supports a simple picture: a universe that expanded rapidly in its earliest moments, then cooled and formed structure over billions of years. Still, the door remains slightly open. Future observations, perhaps with even more sensitive instruments, may uncover subtle signals we have not yet recognized. For now, the oldest light in the sky whispers mostly about inflation, dark matter, and cosmic expansion. But we continue to listen carefully, because if other universes have ever touched ours, if the larger structure of reality has ever left a fingerprint, it may be hidden in that faint, ancient glow, a quiet echo from the earliest chapter of cosmic history. So far, we have explored multiverses that arise from physics, from inflation, quantum mechanics, extra dimensions, and mathematical landscapes. Now we step into a different kind of possibility. What if our universe is not the base level of reality? What if it is a simulation? At first, this idea can sound like science fiction, but it begins with a simple observation about technology. Think about how far computer simulations have come in just a few decades. Early video games showed simple shapes, dots and lines on a flat screen. Today, digital worlds can contain vast landscapes, detailed characters, and complex physics. Some simulations track billions of particles. Some recreate entire cities. Now, imagine technology continuing to improve. If computing power doubles again and again over centuries, simulations could become incredibly detailed, perhaps detailed enough to simulate entire universes. Here is a gentle thought. If a civilization advanced far beyond ours, could they create simulations so realistic that the beings inside would not know they were simulated? It is not impossible in principle. Already we simulate small regions of the universe, tracking how galaxies form or how particles interact. These simulations run on machines the size of rooms. Now imagine a civilization millions of years more advanced. Their computing power could be beyond anything we can currently imagine. To get a sense of scale, think about the number of calculations your brain performs each second. Some estimates suggest it may be around a few trillion operations per second. That sounds enormous. But modern supercomputers already perform many quadrillions of operations per second, thousands of trillions, and technology continues to improve. If computing capacity continues to grow over centuries or millennia, it could reach levels that dwarf today's machines. So here is the quiet question. If advanced civilizations can simulate universes, and if they create many simulations, then statistically, where are we more likely to be? In the one original base reality, or in one of the many simulations? Imagine a vast building with one real room and 1,000 simulated rooms that feel identical from the inside. If you suddenly find yourself conscious inside one of the rooms, the odds suggest you are more likely in one of the simulations. This line of thinking is sometimes called the simulation hypothesis. It does not claim that we are definitely simulated. It suggests that if certain technological paths are possible, then simulated universes may outnumber base universes. And if that is true, we might be inside one. Now pause and consider something important. Even if our universe were a simulation, the physical laws we observe would still operate consistently within it. From our perspective, nothing would feel different. Gravity would still pull, stars would still shine, atoms would still form. The outside reality would be hidden from us. This idea creates a different kind of multiverse. Instead of bubble universes formed by inflation, or branches created by quantum mechanics, there could be many simulated universes running within a higher level reality. Each simulation could have slightly different settings. Some might have stronger gravity, some weaker, some different physical constants. Some might be designed to explore certain questions. And here is an interesting possibility. If simulations can be nested, simulations inside simulations, then reality could have many layers. A civilization inside one simulated universe might eventually develop its own simulations. Those simulations might host their own observers. It would be like a stack of mirrors, reflecting into each other. But now we must ask a calm question. Is there any way to test whether we are in a simulation? Some have suggested looking for signs of computational limits, like a maximum resolution of space and time, similar to pixels on a screen. Interestingly, physics already suggests that space and time may not be infinitely divisible. At extremely small scales, around the Planck length, space may have a minimum size. The Planck length is about 10 to the minus 35 meters. That is so small that if an atom were expanded to the size of the observable universe, the Planck length would still be smaller than a grain of sand in that scale. But whether this reflects computational pixels or simply the structure of quantum gravity is unknown. Others have speculated about detecting glitches, inconsistencies in physical laws. So far, no such evidence has appeared. The laws of physics appear remarkably stable and precise. It is also possible that a sufficiently advanced simulation would be indistinguishable from base reality. From inside, the distinction might be meaningless. Still, the simulation hypothesis adds another layer to the multiverse idea. If advanced civilizations exist and create many simulations, then reality could contain countless artificial universes. And in that case, the multiverse would not just be a product of cosmic inflation or quantum branching. It would be a product of intelligence. Now pause for a moment. If we are inside a simulation, what does that change? On one level, nothing. We still experience life. We still make choices. We still feel joy, curiosity, and wonder. On another level, it shifts the foundation. Our universe would not be the ultimate base layer. It would be one instance among many, whether created for research, entertainment, or purposes beyond our imagination. For now, this idea remains philosophical. It does not emerge directly from established physics, but from reasoning about technology and probability. Still, it reminds us of something important. The multiverse may not only arise from the vastness of space or the branching of quantum events. It may also arise from the possibility that reality itself can be replicated. As we continue, we will explore yet another surprising idea, that black holes might give birth to new universes, creating a kind of cosmic natural selection. For now, let the thought settle gently. If there are other universes, they may not only lie beyond our horizon, they may also exist as countless realities running quietly within a deeper level of existence. Let's return to something very real and very physical. Black holes. Unlike some multiverse ideas that live mostly in equations, black holes are objects we have directly observed. We have seen their influence on nearby stars. We have detected gravitational waves from their collisions. We have even captured images of the glowing matter swirling around them. A black hole forms when a very massive star collapses under its own gravity. Imagine a star many times heavier than our Sun. When it runs out of nuclear fuel, it can no longer support its own weight. Gravity pulls inward with overwhelming force. The core collapses. If the star is massive enough, nothing can stop the collapse. The result is a black hole, a region where gravity is so strong that not even light can escape. To picture this strength, imagine Earth compressed down to the size of a marble. Its gravity at the surface would become so intense that escape would be impossible. For a black hole formed from a massive star, the region from which nothing can escape, called the event horizon, might be only a few dozen kilometers across. That is about the size of a small city, yet inside that small region could be the mass of several suns. Now here is where things become mysterious. According to general relativity, if matter collapses far enough, it forms a singularity, a point of infinite density. But infinite density is a signal that our current theories break down. Physics does not handle infinities well. It suggests that we are missing something. Many physicists believe that quantum gravity, a theory not yet fully developed, would replace the singularity with something more complex. And this opens a door. What if, instead of ending in a singularity, the collapsing matter inside a black hole creates a new expanding region of space? In other words, what if black holes are not just ends, but beginnings? Imagine this. From the outside, a black hole looks like a region where matter disappears. But from the inside, that collapsing matter might bounce into a new expanding space, a new universe. The connection between the parent universe and the new one would be hidden behind the event horizon. From our perspective, we would never see the new universe. It would be cut off from us. But from inside that new universe, the collapse might appear as a big bang. Think about planting a seed in the soil. From the outside, the seed disappears into the ground, but underground, a new plant begins to grow. In this picture, every black hole could be a seed for a new universe. Now pause and consider scale. Our galaxy alone likely contains millions of black holes formed from massive stars, and there are billions of galaxies in the observable universe. That means there could be trillions of black holes. If each one created a new universe, the multiverse would grow through black hole formation. And here is where the idea becomes even more intriguing. Some physicists have suggested a kind of cosmic natural selection. In biological evolution, organisms that reproduce more successfully become more common. If universes give birth to new universes through black holes, then universes that produce more black holes would generate more offspring. Over time, universes with physical constants that favor black hole production would become more common in the multiverse. Interestingly, our universe seems very good at producing black holes. Stars form easily. Many massive stars end their lives in collapse. Galaxies provide environments where black holes can grow. Could this be a coincidence? Or could it be that the constants of our universe are tuned not only for life, but for black hole production? In this scenario, life might be a side effect. The primary selection pressure would be the ability to form black holes. Universes with constants that prevent star formation would produce few black holes and thus few offspring universes. Universes with constants that allow abundant massive stars would produce many black holes and many new universes. It is an elegant and bold idea, but it remains speculative. We do not yet have a complete theory of quantum gravity to describe what truly happens inside a black hole. We do not know whether a bounce occurs or whether a new universe can form. Still, this idea connects the multiverse to something tangible. Black holes are not abstract. They are part of our cosmic landscape. And if they are gateways to new universes, then the multiverse is not just a distant foam of bubbles. It is growing through processes happening all around us. Every time a massive star collapses somewhere in a distant galaxy, a new universe might begin, forever hidden from us, yet part of a larger cosmic tree. Now here is a gentle reflection. If black holes are seeds, then our own universe might have been born from a black hole in another universe. Our Big Bang could be the interior expansion of a collapse that happened elsewhere. That would mean reality is not a single chain, but a branching lineage, a family tree of universes, each born from the death of stars in a parent universe. It is a beautiful symmetry. Stars die, black holes form, new universes begin. Life arises in some of them. Questions are asked again. As we continue, we will explore another model, one in which the universe does not branch outward through black holes, but cycles endlessly through expansion and contraction. For now, let this idea settle softly. In the darkness of a black hole, in a region no light can escape, there may not be an ending. There may be a beginning, hidden from us, but part of a vast and unfolding multiverse. Let's gently shift from black holes to something even larger. Instead of new universes forming inside black holes, what if the entire universe itself goes through cycles? Right now, our universe is expanding. Galaxies are moving away from each other. The farther they are, the faster they recede. This expansion has been happening for nearly 14 billion years. But what if expansion is not the whole story? What if it is just one phase? To understand this idea, imagine throwing a ball straight up into the air. It rises, it slows, it stops, then gravity pulls it back down. For a long time, some scientists wondered whether the universe might behave in a similar way. If gravity were strong enough, it could eventually slow the expansion, stop it, and reverse it. The universe would begin to contract. Galaxies would move closer together. Temperatures would rise. Matter would compress. Eventually, everything might collapse into an extremely dense state, similar to the hot beginning we call the Big Bang. And then, instead of ending, it might bounce. This is sometimes called the Big Bounce. In this picture, the Big Bang was not the absolute beginning. It was the rebound from a previous collapsing universe. Imagine compressing a spring. You push it inward, it stores energy. Then you release it, and it expands outward again. The universe, in this model, behaves like a cosmic spring. Expansion, contraction, bounce, expansion again, over and over. If this process has no true beginning, then our universe is one cycle in an endless series. Now pause for a moment. If the universe cycles forever, does each cycle look the same? Or could each bounce produce slightly different conditions? Some versions of cyclic models suggest that small changes might accumulate. Each cycle could reset certain features but preserve others. Think of waves rolling onto a beach. Each wave looks similar but not identical. The sand shifts slightly each time. Patterns change gradually. In a cyclic universe, the constants might remain mostly stable, or they might shift slightly from one cycle to the next. If that happens, then over many cycles a kind of variation could emerge. But there is an important detail. Recent observations show that the expansion of the universe is accelerating. This acceleration is driven by something we call dark energy, a mysterious component that makes up about 70% of the total energy content of the universe. Dark energy acts like a repulsive force. Instead of slowing expansion, it speeds it up. To picture this, imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move apart. Now imagine that instead of inflating steadily, the balloon expands faster and faster over time. That is similar to what we observe. If dark energy continues to dominate, the universe may not collapse at all. It may expand forever. However, some cyclic models incorporate dark energy in creative ways. They suggest that dark energy might eventually reverse or transform, allowing contraction to begin. Other models propose that the bounce does not require full contraction to a singularity. Instead, quantum gravity effects at extremely high densities could cause a rebound before infinite density is reached. This is similar to how quantum mechanics prevents electrons from collapsing into the nucleus of an atom. Certain quantum effects create pressure that resists complete collapse. In the Big Bounce idea, similar effects might prevent a true singularity. Now here is a gentle question. If the universe cycles endlessly, could traces of previous cycles survive? Some researchers have searched for subtle patterns in the cosmic microwave background that might hint at events before the Big Bang, signals carried across the bounce. So far, no clear evidence has been found. The data remains consistent, with a single hot beginning, but the possibility remains open. The cyclic model offers something emotionally powerful. It removes the idea of an absolute beginning. Instead of asking, what happened before the Big Bang? The answer becomes another universe, and before that, another. It stretches backward without a starting point, like a circle with no beginning or end. It also changes how we think about time. Instead of a straight line starting at a single point and moving forward forever, time becomes rhythmic, breathing in, breathing out, expansion, contraction. If this is true, then our universe is not a solitary event in an empty void. It is one beat in an endless cosmic rhythm. Now imagine this quietly. Long before our stars formed, another universe may have expanded, cooled, formed galaxies, perhaps even life, then slowly contracted, collapsed, bounced, and from that bounce, our universe began. In the distant future, trillions of years from now, long after our sun has faded, the cycle might continue again. It is a calm and steady image, not explosive, not chaotic, just a universe that renews itself endlessly. As we move forward, we will explore another idea that goes even deeper into abstraction, the suggestion that reality itself may be identical to mathematics. But for now, let this thought rest gently. The Big Bang may not have been the first chapter. It may have been the latest sunrise in a universe that has been rising and falling forever. Let's move even deeper. So far, we have imagined universes branching through inflation, splitting through quantum events, emerging from black holes, cycling through bounces, or existing as simulations. Now we arrive at a quieter but more radical thought. What if reality is mathematics, not described by mathematics, not modeled by mathematics, but actually is mathematics? To understand this, start with something simple. When physicists describe gravity, they use equations. When they describe how light bends around a star, they use geometry. When they describe particles, they use mathematical objects and relationships. Again and again, the universe appears to follow mathematical patterns. If you measure the orbit of a planet, its motion fits precise equations. If you study how atoms absorb light, the energy levels come in exact numerical steps. Even the structure of space-time, how it curves and stretches, is described by mathematical formulas. This raises a quiet question. Why is mathematics so effective at describing reality? It is almost mysterious. The symbols on a chalkboard, abstract numbers and shapes, somehow capture the behavior of stars millions of light years away. Imagine writing an equation on paper in a small room, and that equation predicts how a galaxy rotates across billions of kilometers of space. That connection feels deep. Some physicists suggest that the reason mathematics works so well is because reality is a mathematical structure. In other words, the universe does not just obey equations, it is an equation. Or more accurately, it is a structure defined by mathematical relationships. To picture this gently, think about a chess game. The board has rules, the pieces have allowed moves. The game unfolds according to those rules. Now imagine that instead of wood and carved pieces, the entire game exists purely as relationships. patterns of position and motion defined by rules. In the same way, our universe could be a set of relationships, particles interacting, fields fluctuating, space curving, all governed by mathematical consistency. In this view, physical existence and mathematical existence are the same thing. If a mathematical structure is self-consistent, meaning it does not contradict itself, then it exists physically as a universe. That idea leads to something profound. There are countless mathematical structures, simple ones like the geometry of a circle, more complex ones like higher dimensional spaces, abstract systems defined by sets of rules. If every consistent structure exists physically, then the multiverse becomes vast beyond imagination. Not just variations of our laws, not just different constants, but entirely different kinds of realities defined by different mathematical foundations. Some might have more dimensions, some fewer. Some might have entirely different relationships between space and time. Some might not resemble anything we can picture. Imagine a library containing every logically consistent rulebook for reality. Each rulebook defines a universe. In one, gravity behaves as it does here. In another, the rules of interaction are entirely different. Now here is the quiet question. Why do we experience this particular mathematical structure? In this hypothesis, there is no deeper reason. We exist in this structure because it allows observers like us to emerge. In other structures, no observers arise. It becomes another extension of the anthropic idea. Observers exist only in structures where self-aware patterns conform. It is similar to how certain equations produce stable shapes, while others produce chaos. If you draw mathematical patterns on a computer, some generate intricate, stable fractals. Others collapse into noise. We inhabit a structure that allows stability, complexity, and consciousness. But there may be countless structures that do not. Now pause and consider scale. Earlier, we spoke about numbers like 10 to the power of 500, possible configurations in string theory. That was already enormous. But the space of all mathematical structures is even larger. It is not just a vast landscape. It is potentially unbounded. And in this view, our universe is one point in that abstract space. It feels almost poetic. Reality as a mathematical pattern that is aware of itself. Atoms form molecules. Molecules form cells. Cells form brains. Brains form thoughts. And those thoughts reflect on the mathematical structure that gave rise to them. It is like a pattern within a pattern, becoming aware of the rules that define it. But there is a challenge. How could we ever test whether all mathematical structures exist physically? Unlike inflation or quantum mechanics, this idea may not produce specific experimental predictions. It moves closer to philosophy. Still, it offers a powerful perspective. Instead of asking why the laws of physics are what they are, it suggests that all possible laws exist somewhere. We find ourselves in one of the structures where complexity is possible. It removes the need for uniqueness. It removes the need for a special explanation. It says, mathematical consistency is enough. And wherever consistent structures allow observers, those observers will ask why they are there. As we continue, we will turn to a more grounded concern, whether any of these multiverse ideas can be tested at all. Because no matter how elegant a theory feels, science depends on evidence. For now, let this thought rest softly. The universe may not just follow mathematics. It may be mathematics, a vast, self-consistent structure within a boundless landscape of other possible structures, all equally real in their own quiet way. We have traveled far, across inflation and quantum branches, across extra dimensions and black holes, across cycles and mathematical landscapes. Now we arrive at a calm but important question. Can any of this be tested? Science is not only about imagination, it is about observation, measurement, and prediction. A scientific idea must in principle make predictions that could be proven wrong. If there is no possible observation that could challenge it, then it begins to drift away from science and toward philosophy. So where does the multiverse stand? Let's take this gently. The simplest version, more space beyond our observable horizon, is difficult to test directly. By definition, regions beyond our horizon cannot send light to us. No matter how powerful our telescopes become, we cannot see past that boundary. It is like standing in a valley surrounded by mountains. You may strongly suspect that land continues beyond the peaks, but unless you climb over them, you cannot confirm it. However, this idea is closely tied to inflation, and inflation itself makes testable predictions about the flatness of space and the pattern of fluctuations in the cosmic microwave background. Those predictions have been confirmed with impressive precision, so while we cannot directly observe regions beyond our horizon, the theory that implies them has passed several tests. That gives it some scientific weight. Now consider eternal inflation and bubble universes. These ideas arise naturally from certain versions of inflation theory, but detecting other bubbles is extremely difficult. We discussed the possibility of collisions leaving imprints in the cosmic microwave background. So far, no confirmed evidence has appeared. If such evidence were found, a clear, unmistakable pattern inconsistent with other explanations, it would strongly support the multiverse picture. But until then, bubble universes remain unobserved. What about the many worlds interpretation of quantum mechanics? Quantum theory itself is incredibly well tested. It predicts experimental outcomes with astonishing accuracy, often to more than 10 decimal places. But the many worlds interpretation does not change those predictions. It offers a different explanation of what the mathematics means. From the outside, experiments cannot easily distinguish between wave function collapse and branching realities. Both interpretations produce the same measurable results. So the question becomes philosophical rather than experimental. Do we accept multiple branches as real, or do we assume collapse? Both fit the data. Now consider string theory in the landscape. String theory is mathematically rich. It unifies forces in elegant ways. But so far, it has not produced unique predictions that can be tested with current technology. The energy scales, where strings would become directly visible, are far beyond what our particle accelerators can reach. To give you a sense of scale, the Large Hadron Collider accelerates particles to energies of trillions of electron volts, but string effects may appear only at energies billions of times higher. It would be like trying to observe details on a grain of sand from the other side of the Earth. So string theory's multiverse implications remain theoretical. The simulation hypothesis faces a similar challenge. If our universe were simulated with perfect consistency, it might be impossible to detect any difference from base reality. Any glitch could simply be reinterpreted as a new physical law. In that case, the hypothesis might not be falsifiable. Now here is the deeper issue. If a theory predicts the existence of countless universes that we can never observe, does that weaken its scientific status? Some physicists argue yes. They worry that invoking unseen universes to explain fine-tuning is like adding invisible elements to avoid deeper questions. Others argue that if the multiverse arises naturally from well-tested theories, then we cannot ignore it simply because it is difficult to observe. It becomes part of the overall framework. Think about atoms. Before microscopes could see them, atoms were inferred from patterns in chemistry. Scientists could not observe them directly, but the theory made predictions that worked. Eventually, technology caught up. Perhaps the multiverse is similar. We may not yet have the tools to test it fully, or perhaps it will always remain partly beyond reach. Science sometimes advances by exploring ideas that seem unreachable at first, but it also demands humility. We must distinguish between what is supported by evidence and what remains speculative. The multiverse sits in that delicate space, Parts of it are tightly linked to established physics. Other parts extend far beyond what we can confirm. So where does that leave us? It leaves us curious, but cautious, open to possibility, but grounded in observation. As we move toward the final reflections of this journey, we will explore the voices of critics, scientists who argue that the multiverse may not be necessary, or may not belong within physics at all. For now, let this rest. The question, are there other universes, is not only about imagination, it is also about the boundaries of science itself. How far can explanation stretch? How much can we infer from theory? And when does a beautiful idea become something more than science can test? These questions are part of the journey, and they remind us that curiosity must walk hand in hand with careful thought. After traveling through so many possibilities, it is only fair to pause and listen to the other side. Not everyone in physics is convinced that the multiverse is the right path. Some scientists argue that the idea stretches too far beyond what we can observe. Their concern is not about imagination. Science thrives on bold ideas. The concern is about testability and necessity. Let's gently explore their perspective. One argument is simple. If other universes can never interact with ours, if no signal can reach us, no collision can be detected, no experiment can reveal them, then how is the idea different from speculation? Science, at its core, relies on observations that can confirm or challenge a theory. Imagine someone claims there is an invisible dragon in their garage. If the dragon cannot be seen, heard, touched, or detected in any way, the claim becomes impossible to test. Some critics worry that certain versions of the multiverse resemble that situation. If bubble universes lie forever beyond our cosmic horizon, and if branching quantum worlds can never be observed directly, then are we stepping outside the boundaries of physics? Another concern relates to fine-tuning. The multiverse is often used to explain why physical constants fall within life-friendly ranges. Instead of searching for a deeper underlying law that fixes those constants, the multiverse suggests that many values exist across many universes, and we happen to be in one that allows life. Critics ask, is this explanation too convenient? It is like noticing that a dart landed in the center of a target and saying, there must be countless targets out there. We just happened to hit one. Maybe that is true, but maybe the dart was aimed carefully. Some physicists prefer to keep searching for deeper principles that uniquely determine the constants of nature. History offers examples where apparent fine-tuning was later explained by deeper theory. At one time, the orbits of planets seemed arbitrary. Later, gravity provided a unifying explanation. At one time, the properties of atoms seemed mysterious. Later, quantum mechanics revealed the structure beneath. So critics argue that giving up too soon by invoking many universes might slow the search for deeper understanding. There is also a psychological dimension. The multiverse can make our universe feel less unique. If there are infinite universes, each with variations, then our cosmic story becomes one among many. Some see this as a natural extension of previous discoveries. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the only galaxy. Why should our universe be unique? Others feel that multiplying universes without direct evidence risks making physics less grounded. It can feel like adding layers of abstraction when simpler explanations might still exist. Now here is a calm question. Are critics rejecting the multiverse because it is uncomfortable, or because it truly lacks scientific grounding? The answer depends on which version we are discussing. The simplest extension, more space beyond our observable horizon, is widely accepted. Few physicists doubt that space likely continues beyond what we can see. Eternal inflation, tied closely to well-supported inflation theory, has more support but remains unconfirmed. The many worlds interpretation divides physicists more evenly. Some embrace it as the cleanest reading of quantum mechanics. Others prefer interpretations involving collapse. The more radical ideas, like the mathematical universe or simulation hypothesis, are viewed by many as philosophical rather than scientific. So the criticism is not uniform. It varies depending on how far the idea stretches. But beneath all these debates lies a deeper theme. Science evolves. Ideas that once seemed outrageous sometimes become accepted. Others fade away. The multiverse sits at the edge, neither fully established nor fully dismissed. And perhaps that is where it belongs for now. Now imagine standing at the shoreline at night. You see waves gently touching the sand. Beyond the reach of moonlight, the ocean extends into darkness. Some people are content to study the waves they can see. Others feel drawn to imagine what lies beyond the horizon. Both instincts are part of science. Careful measurement, bold speculation. The critics remind us to stay grounded. They remind us that beauty and elegance are not proof. At the same time, the existence of critics does not erase the multiverse. It keeps the conversation balanced. As we approach the final reflections of this journey, we will ask a different kind of question. Even if other universes exist, could we ever reach them? Or are they forever separated from us by the structure of space and time? For now, let this settle gently. The multiverse is not a settled fact, it is a frontier. And like all frontiers, it invites both excitement and caution, both curiosity and skepticism. And perhaps that balance is exactly what keeps science moving forward. After everything we have explored, a very human question rises quietly. If other universes exist, could we ever go there? It is the same instinct that once made people look at the horizon and wonder what lay beyond the sea. The same instinct that eventually carried humans to the moon. So, let's approach this gently. First, consider the simplest multiverse idea, regions beyond our observable universe. If space continues forever beyond our cosmic horizon, could we travel there? The answer, based on what we understand today, is no. The universe is expanding, and not just expanding, but accelerating. Distant galaxies are moving away from us, faster and faster. Some are receding so quickly that their light will never reach us, no matter how long we wait. To picture this, imagine standing on an escalator that is moving downward, faster than you can run upward. No matter how hard you try, you cannot reach the top. In the same way, the expansion of space creates a boundary. Even if we built a spacecraft traveling close to the speed of light, 300,000 kilometers per second, we would still be unable to reach regions beyond a certain distance. The expansion would carry them away too quickly. Now consider bubble universes formed through eternal inflation. These bubbles would be separated by space expanding faster than light could cross. They are not just far away, they are cut off by the structure of space-time itself. Even light cannot bridge that gap. And if light cannot, then no physical object can. What about quantum branches, the many worlds picture? If reality branches into parallel histories at every quantum event, could we somehow step into another branch? Here, the separation is not spatial but quantum. Once branches split, they no longer interact. It is like two radio stations broadcasting on different frequencies. You can tune into one or the other, but you cannot merge them. The mathematics of quantum mechanics suggests that once decoherence occurs, once branches separate, they effectively become isolated. There is no known way to reverse that process. No door, no bridge. Now let's turn to extra dimensions. If other universes exist on nearby branes in higher dimensional space, could we move into that hidden direction? In theory, extra dimensions might be extremely small, curled up at scales far smaller than atoms. To access them, we would need energies far beyond anything we can currently produce. Even the most powerful particle accelerator on Earth stretching for 27 kilometers in a circular tunnel, cannot reach the energy scale where extra dimensions might reveal themselves. To reach those scales, we might need a machine larger than our solar system. And that is not a practical engineering challenge. It is a boundary of physics as we currently understand it. What about wormholes? General relativity allows solutions that resemble tunnels through space-time, shortcuts connecting distant regions. In science fiction, wormholes often connect separate universes, but here is the calm reality. Even if wormholes are mathematically possible, we have no evidence that stable, traversable wormholes exist, and keeping one open might require exotic forms of matter with negative energy, something we have not observed in the necessary quantities. So far, wormholes remain theoretical curiosities. What about black holes as gateways? If black holes give birth to new universes, could we travel through one? From our perspective, crossing the event horizon of a black hole leads inevitably toward extreme gravitational forces. For a small black hole, the tidal forces near the event horizon would stretch you like a strand of spaghetti, a process sometimes called spaghettification. For a supermassive black hole, millions or billions of times heavier than the Sun, the event horizon might be gentler at first. But once inside, the path leads inward, with no return. And even if a new universe forms beyond, it would be causally disconnected from ours. There would be no path back. Now pause and ask gently, if we cannot reach other universes physically, does that make them irrelevant? Not necessarily. Even if we cannot visit them, understanding whether they exist changes how we see our own universe. When sailors first realized Earth was round, it changed their understanding of geography. Even before they sailed around the globe, knowledge reshapes perspective. The multiverse may be similar. Reaching other universes may be impossible, not because we lack technology, but because reality itself prevents communication across those boundaries. The limits are not practical. They are structural. Space-time itself forms the barrier. Still, human imagination naturally pushes against limits. We imagine shortcuts, hidden dimensions, future technologies beyond our current understanding. History shows that many boundaries once thought impossible were eventually crossed. But some boundaries may be fundamental. Just as no object can exceed the speed of light in our current understanding of physics, there may be no mechanism to cross into separate universes. For now, every serious physical model suggests isolation. Other universes, if they exist, are not neighboring countries we might one day visit. They are separate realms, divided by the architecture of reality itself. And perhaps that is part of what makes the question so profound. Other universes may exist, but they may forever remain beyond our reach, not hidden by distance alone, but by the deep structure of space, time, and causality. As we approach the final reflection, we will turn inward once more. If there are countless universes, infinite variations, infinite possibilities, what does that mean for us? For identity, for meaning, for uniqueness? For now, let this thought rest softly. The multiverse, if real, may not be a destination. It may be a horizon, one that shapes how we see everything. Even if we never cross it, we have traveled far together, across expanding bubbles, cross-branching realities, across hidden dimensions and cosmic cycles. Now we arrive at the quietest part of the journey. If other universes exist, what does that mean for us? Not in equations, not in distant galaxies, but here, in this moment. One of the first thoughts people often have is personal. If there are infinitely many universes, could there be another version of you? In some multiverse models, especially those involving infinite space or quantum branching, the answer could be yes. If space is infinite, and if matter can only arrange itself in a limited number of ways within a region the size of our observable universe, then eventually patterns repeat, somewhere unimaginably far away, far beyond 93 billion light years, beyond numbers we can meaningfully describe. There could be a region where atoms are arranged exactly as they are here, a planet like Earth, a room like this one, a person like you, perhaps making slightly different choices, perhaps identical up to this very second. It feels unsettling at first. If there are infinite versions of you, does that make this version less special? But pause for a moment. Even if copies exist somewhere, you experience only this branch, this moment, this perspective. Your thoughts are happening here. Your awareness is anchored here. If a copy exists beyond any possible interaction, separated by distances that light itself cannot cross, then from your lived experience, it does not change your uniqueness. It is like two identical books printed in different cities. Each copy still contains its own story in its own place. Now consider another possibility. If there are countless universes with different outcomes, then every success and every failure might occur somewhere. In one universe, a star forms. In another, it does not. In one branch, a choice leads one way. In another, a different way. Does that make your choices meaningless? Or does it make them more precious? From inside your own path, the decisions you make shape your lived experience. Even if another branch exists where you chose differently, you do not experience that branch. Meaning arises from perspective. Think about reading a novel. Even if the author writes multiple alternate endings, the version you read still carries emotional weight. The characters still struggle, hope, and change. Your life is not diluted by the existence of other possibilities. It is defined by the path you walk. There is another deeper question. If the multiverse is real, are we insignificant? If there are infinite universes, infinite stars, infinite worlds, does our small planet lose importance? But consider this. Even within a single universe containing billions of galaxies, your experiences matter to you. Scale does not erase significance. A single note in a symphony may be small compared to the whole orchestra, but without it, the music changes. A grain of sand on a beach is tiny, but remove enough grains, and the shape of the shoreline shifts. Meaning is not measured by size, it is measured by experience. If the multiverse exists, it may make reality larger than we imagined, but it does not erase the depth of a single moment of awareness. In fact, it may do the opposite. It may remind us how extraordinary it is that conscious beings arise at all. Across all possible universes, across all possible constants and laws, there may be vast regions of emptiness, cold, dark, lifeless. And yet here, in this universe, on this small planet orbiting an average star, matter has organized itself into forms that can reflect on the cosmos. Atoms that once burned in ancient stars now form thoughts. That is remarkable. Whether or not there are other universes, now consider another gentle perspective. If reality is larger than we imagine, far larger, then humility becomes natural. We are not at the center. We are not the only story. We are part of something vast, but being part of something vast does not make us irrelevant. It makes us participants. The multiverse, if real, expands the canvas. It does not erase the painting. It invites a shift from why is everything about us to what is our place in something much greater. And perhaps that is the deeper gift of this question. The question, are there other universes, stretches the mind beyond familiar boundaries. It loosens the idea that what we see is all that exists. It encourages curiosity. It reminds us that reality may be layered, expansive, and still partly unknown. And even if the multiverse remains unconfirmed, even if we never detect another universe, the act of asking changes us. It trains us to think beyond limits, to look at the night sky and feel not just smallness, but connection. Connection to something vast and unfolding. In the end, Whether there is one universe or infinitely many, we are here, aware, curious, looking outward. If there are countless universes, we are one expression among many. If there is only one, we are part of something singular and precious. Either way, the mystery remains beautiful. And perhaps that is enough. So, as you rest with this thought, imagine the possibility, not as something distant and cold, but as an expansion of wonder. Reality may be far larger than we imagine, and within that vastness, here you are, a small, conscious pattern in a cosmic structure, asking questions about the whole.